If you watch the first 200 facts in this series, you already know the universe is stranger than it looks. This is the sequel, and every single fact tonight is new. We're starting with a rock the size of a mountain that carries the name of the day it will make its closest known pass by Earth, moving on to a star system where 7 planets orbit so closely together that from the surface of one you could watch the others cross the sky like a slow-motion eclipse, and ending somewhere past the edge of string theory's own bewildering mathematics, where physicists have calculated that there may be more possible versions of physical law than there are atoms in the observable universe, and no experiment yet devised that can tell us which one, if any, is actually real. In between, we'll cover the antimatter that should have annihilated all matter in the universe within the first second after the Big Bang and somehow didn't, the ghost particles passing through your body by the trillions every second without ever touching anything, and the single subatomic measurement that has quietly outperformed every other prediction in the history of physics by 14 decimal places, and still doesn't quite match what theory says it should. 300 more facts, 3 more hours, and not one repeated word from where we left off. Let the universe once again carry you slowly toward sleep. Not everything orbiting the sun formed neatly into planets, and the solar system's leftover material, the asteroids, comets, and countless smaller fragments still drifting through it, today turns out to hold some of the most genuinely unresolved puzzles anywhere in our own cosmic backyard, questions that have only grown more numerous as observation technology has improved enough to actually find and study these objects in real detail. The asteroid belt, sitting between the orbits of Mars and Jupiter, was long assumed by earlier generations of astronomers to be the shattered remains of a planet that never quite formed, or that formed and was later destroyed, a popular idea that modern research has largely overturned, without ever having been definitively laid to rest. Current models suggest the belt's total mass, even combining every object within it, amounts to less than 4% of the mass of Earth's own moon, far too little material to have ever assembled into a full planet in the first place. And the leading explanation now holds that Jupiter's immense gravity, forming and growing nearby during the solar system's earliest chaotic period, gravitationally stirred the region so thoroughly that any planetesimals attempting to coalesce there were repeatedly flung apart or ejected entirely before they could grow much larger than the dwarf planet Ceres, the largest object in the belt today, at roughly 940 kilometers across. Precisely how much material Jupiter's early migration through the solar system removed from this region, and exactly how the belt's current, considerably depleted population relates to whatever original disk of material once orbited there, remains an active subject of ongoing simulation work, rather than a fully settled question. Comets present an entirely different kind of mystery, since unlike asteroids, which are generally rocky or metallic bodies that have remained close to the sun for the solar system's entire history, comets are believed to originate primarily from 2 considerably more distant reservoirs: the Kuiper Belt, a disk of icy bodies extending beyond Neptune's orbit, and the Oort cloud, a theorized spherical shell of icy material believed to surround the entire solar system at distances of up to 2 light-years from the sun, roughly halfway to the nearest star. The Oort cloud's existence remains notably an inference rather than a direct observation. No telescope has ever directly imaged an Oort cloud object at its theorized distance, since objects there would be far too small, far too cold, and far too distant to reflect enough sunlight for any current instrument to detect, meaning the entire concept rests on indirect evidence, primarily the observed orbital paths of long-period comets that swing in from seemingly random directions with orbital periods stretching into the thousands or even millions of years, paths that make the most physical sense if they originate from a roughly spherical distant reservoir rather than any flatter, more organized structure closer to the sun. Halley's Comet, the most famous periodic comet known to naked eye observers throughout recorded human history, offers a useful illustration of just how much modern spacecraft visits have complicated earlier, simpler assumptions about what comets actually are. When the European Space Agency's Giotto spacecraft flew past Halley's Comet in March 1986, capturing the first close-up images ever taken of a comet's nucleus, it revealed a body considerably darker than almost anything else in the solar system, reflecting only about 4% of the sunlight striking it, roughly as dark as fresh asphalt, and shaped like an irregular, elongated potato rather than any kind of clean sphere. This surprisingly dark, carbon-rich surface, now confirmed across numerous other comets visited by later missions, remains only partially explained, with leading hypotheses pointing to a crust of complex organic compounds gradually built up and darkened by billions of years of exposure to cosmic radiation, though the precise chemical pathway producing such a uniformly dark surface across so many independently formed comets remains an active subject of laboratory and observational research. The risk that a sufficiently large asteroid or comet might strike Earth directly is not, it's worth saying plainly, a purely theoretical concern confined to disaster films. On June 30, 1908, an object believed to be either a small asteroid or a fragment of a comet exploded in the atmosphere above the Podkamanaya Tunguska River in a remote region of Siberia, releasing energy estimated at somewhere between 10 and 15 megatons, roughly 1,000 times more powerful than the atomic bomb dropped on Hiroshima, and flattening an estimated 80 million trees across roughly 2,150 square kilometers of forest, an area larger than the City of London. Because the object exploded in the air rather than striking the ground directly, and because the impact occurred in such a remote, sparsely populated region, no confirmed human casualties resulted, and no impact crater has ever been definitively identified at the site, leaving the exact size, composition, and precise origin of the Tunguska object a subject that continues to generate published research and, occasionally, genuine scientific disagreement more than a century later. Before we go on, if you're the kind of person who likes falling asleep to 3 hours of the universe's leftover mysteries, this channel puts one of these together regularly, and subscribing costs nothing, and just means the next one finds you automatically. Now back to the solar system's own quiet debris field. A considerably more recent and considerably better documented event occurred on February 15, 2013, when a meteor roughly 20 meters across entered the atmosphere over Chelyabinsk, Russia, at a speed of approximately 19 kilometers per second, exploding with an estimated force of around 500 kilotons at an altitude of roughly 30 kilometers, an explosion bright enough to be captured on hundreds of dashcam videos, since the object arrived without any advance warning from any of the world's asteroid tracking programs, and the resulting shockwave shattered windows across 6 Russian cities, injuring more than 1,600 people, primarily from flying glass, though causing no confirmed deaths. The Chelyabinsk event became, almost overnight, one of the most thoroughly documented meteor impacts in history, specifically because of the sheer volume of amateur dashcam and security camera footage capturing it from dozens of different angles, footage that allowed scientists to reconstruct the object's trajectory, composition, and explosive yield with a precision no comparable historical impact event has ever matched, and that meaningfully accelerated international funding for automated near-Earth object detection systems specifically designed to catch objects of this size before they arrive with no warning at all. Modern planetary defense efforts received their first genuine real-world test on September 26, 2022, when NASA's Double Asteroid Redirection Test, commonly abbreviated DART, deliberately crashed a roughly 570-kilogram spacecraft directly into Dimorphos, a small moonlet, orbiting the larger asteroid Didymos, specifically to test whether a kinetic impact could meaningfully alter an asteroid's orbital path, a proof of concept for a potential future planetary defense technique against a genuinely hazardous incoming object. The impact successfully shortened Dimorphos's orbital period around Didymos by approximately 32 minutes, considerably more than mission planners had conservatively projected beforehand. A result NASA formally declared a success, and one that provided the first direct, real-world confirmation that humanity possesses at least one workable technique for altering the path of a hazardous asteroid. Though scientists studying the aftermath noted, the impact also produced an unexpectedly large debris trail and a measurable, still not fully explained wobble in Dimorphos's subsequent rotation, effects that continue to be analyzed for what they reveal about the asteroid's internal structure, composition. Interstellar visitors passing directly through our solar system remain vanishingly rare in the confirmed observational record, and the second one ever detected, discovered on August 30, 2019 by amateur astronomer Gennady Borisov and formally designated 2I, Borisov, offered a genuinely useful point of comparison against the peculiarities of the first confirmed interstellar object. Unlike its predecessor, Borisov's comet behaved, in most observed respects, remarkably similarly to comets that originated within our own solar system, developing a normal dusty cometary tail and showing a chemical composition dominated by carbon monoxide at unusually high levels, broadly consistent with comets, formed around other young stars, evidence that at least this particular interstellar wanderer likely formed through processes genuinely similar to those that build comets here at home, even as it arrived from, and eventually departed back, toward a star system no telescope has ever definitively identified. NASA's New Horizons spacecraft, the same mission responsible for the Pluto and Karanchkan findings covered in the first installment of this series, achieved a second and considerably less publicized milestone on January 1, 2019, when it flew past a small, distant Kuiper Belt object formally designated 486,958 Arrokoth, becoming the most distant object any spacecraft has ever visited up close. At roughly 6.6 billion kilometers from the Sun, Arrokoth turned out to be a genuine, contact binary, two separate lobes of primordial material that gently merged together at extraordinarily low speed sometime in the solar system's earliest history and have remained fused together, essentially undisturbed, ever since, making it, according to mission scientists, the most pristine and least altered object ever directly studied by any spacecraft, a genuine, frozen snapshot of the raw material the outer solar system's planets originally formed from, preserved specifically because Arrokoth's extreme distance and correspondingly extreme cold have shielded it from nearly every process that would otherwise have altered a comparable object closer to the Sun over the following 4.6 billion years. A separate and genuinely underappreciated category of solar system object, called centaurs, orbits in the gravitationally unstable region between Jupiter and Neptune, crossing the orbits of the outer gas giants directly, and these objects, named after the mythological creatures that were part one thing and part another, behave as a genuine transitional category between the icy Kuiper Belt bodies discussed above and the more familiar short-period comets that swing in close to the Sun. Chiron, the first centaur ever discovered, identified in 1977, was initially classified simply as an unusually distant asteroid, before later observations revealed it periodically develops a genuine cometary coma, a hazy envelope of gas and dust, blurring the traditional distinction between asteroid and comet entirely, and forcing astronomers to formally acknowledge that the two categories exist on a genuine continuum rather than as two cleanly separated types of object, a reclassification that has since been applied to a growing number of similarly ambiguous centaur objects discovered in the decades since. A further blurring of the traditional asteroid-comet boundary comes from 3200 Phaethon, discovered in 1983, and notable for two genuinely distinctive traits at once. It's the confirmed parent body of the Geminid meteor shower, the reliable mid-December display visible from Earth every year, and yet it's formally classified as an asteroid rather than a comet, since it shows no visible coma or gas tail through most of its orbit. What makes Phaethon a genuine outlier is that it periodically develops a brief, faint dust tail during the portion of its orbit that brings it closest to the Sun, a distance close enough to heat its rocky surface to roughly 750 degrees Celsius, hot enough that researchers studying the object, including a dedicated 2018 study using NASA's Stereo solar observing spacecraft, now believe the tail is produced by thermal fracturing and sodium vaporization directly from Phaethon's rocky surface, a fundamentally different physical process than the ice sublimation that produces a genuine comet's tail, earning Phaethon the informal nickname Rock Comet and making it, alongside the centaurs discussed above, a further practical demonstration that the clean textbook line separating asteroids from comets describes a convenient simplification rather than a genuine, sharp division found in nature. For the entire span of recorded human history before 1995, not a single planet orbiting a star other than our own Sun had ever been confirmed to exist, despite centuries of philosophical speculation that such worlds must surely be out there somewhere. That changed on October 6, 1995, when Swiss astronomers Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b, a planet orbiting a Sun-like star roughly 50 light-years away, detected through subtle periodic wobbles in the star's own light caused by the planet's gravitational tug, a technique called the radial velocity method. The discovery itself immediately produced a genuine puzzle that reshaped planetary science almost overnight. 51 Pegasi b turned out to be a gas giant roughly half the mass of Jupiter, orbiting its star in just 4 days, at a distance closer than Mercury orbits our own Sun. A configuration existing planet formation theory, built entirely around our own solar system's example, had never predicted and initially struggled to explain at all, giving rise to an entirely new category of world astronomers now called hot Jupiters. Mayor and Queloz shared the Nobel Prize in Physics in 2019 for the discovery. NASA's Kepler Space Telescope, launched in March 2009 and operating continuously until its retirement in 2018, transformed exoplanet science from a field of scattered individual discoveries into a genuine statistical science, staring fixedly at a single patch of sky containing roughly 150,000 stars and detecting the tiny, periodic dimming that occurs when a planet passes directly in front of its host star from Earth's perspective, a technique called the transit method. By the end of its mission, Kepler had confirmed more than 2,600 exoplanets and identified several thousand additional candidates still awaiting formal confirmation, and its most significant statistical finding, extrapolated across the full galaxy, suggested that the Milky Way likely contains more planets than stars, with a meaningful fraction of Sun-like stars hosting at least one roughly Earth-sized planet orbiting within their star's habitable zone, the specific orbital distance range where liquid water could plausibly exist on a rocky world surface. The TRAPPIST-1 system, announced in February 2017 by a research team using the TRAPPIST telescope in Chile, alongside follow-up observations from the Spitzer Space Telescope, offers one of the single most remarkable planetary configurations ever confirmed: 7 roughly Earth-sized rocky planets orbiting an ultra-cool red dwarf star just 40 light-years away, packed so tightly together that their orbits all fit within a distance smaller than Mercury's own orbit around our Sun, at least 3, and by some habitable zone calculations as many as 4. Of the 7 TRAPPIST-1 planets orbit within a range where liquid water could theoretically exist, and the planets sit close enough to each other that, from the surface of any one of them, several of its neighboring worlds would appear in the sky larger than our own moon appears from Earth, occasionally passing directly in front of each other in a kind of slow, visible planetary choreography. Whether any of these worlds actually retain a meaningful atmosphere at all, given how close they orbit an active, flare-prone red dwarf star, remains a genuinely open and actively studied question, with James Webb Space Telescope observations published beginning in 2023, finding, somewhat discouragingly, no strong evidence of a substantial atmosphere around the innermost planets studied so far, a finding that has meaningfully tempered some of the system's earlier habitability, optimism, without fully resolving the question for the system's more distant members. Proxima Centauri b, announced in August 2016, holds the distinction of being the closest known exoplanet to our own solar system, orbiting Proxima Centauri, the nearest star to the Sun, at just over 4 light-years away, within what astronomers calculate to be that star's habitable zone. Proxima Centauri itself is a small, dim red dwarf star prone to powerful, unpredictable flares, including one recorded in 2019 that briefly increased the star's brightness by a factor of 14,000, a stellar outburst so severe that many astronomers now consider it a serious open question whether any planet orbiting close enough to sit within Proxima Centauri's narrow habitable zone could retain a stable atmosphere at all across geological timescales, given the sheer, repeated intensity of radiation such flares would deliver. A genuine tension between orbital distance and stellar temperament that recurs across a considerable number of the potentially habitable worlds discovered around similarly small, similarly volatile red dwarf stars, which happen to be the most common type of star in the entire galaxy. Detecting an exoplanet's atmosphere directly, rather than merely inferring the planet's existence from its gravitational or transit signature, became a genuinely practical scientific technique only with the James Webb Space Telescope's launch in December 2021, and the results published since have opened up an entirely new category of unresolved question. When a planet transits directly in front of its host star, a small fraction of the star's light passes through the planet's atmosphere on its way to Earth's telescopes, and different atmospheric gases absorb very specific wavelengths of that light, allowing astronomers to determine an exoplanet's atmospheric composition from tens or even hundreds of light-years away, a technique called transmission spectroscopy. This method has already produced genuinely surprising individual results, including the detection of carbon dioxide, water vapor, and, in a particularly debated 2023 finding, regarding the exoplanet K2-18b, a candidate detection of dimethyl sulfide, a chemical compound that on Earth is produced almost exclusively by living organisms, a finding the research team itself explicitly described as preliminary and requiring considerably more data before any confident interpretation could be drawn, a case we'll return to with the appropriate caution in a later chapter of tonight's video specifically dedicated to biosignatures, the sheer diversity of confirmed exoplanet types discovered since 1995 has itself become one of the field's most genuinely humbling lessons, repeatedly overturning assumptions astronomers had built almost entirely around our own solar system's single available example. Astronomers have now confirmed so-called super-Earths, rocky planets larger than Earth but smaller than Neptune, a category, with no direct analog anywhere in our own solar system at all, along with many Neptune's ocean worlds theorized to be entirely covered by liquid water hundreds of kilometers deep, and even a small number of candidate diamond planets, carbon-rich worlds where astronomers have proposed that extreme internal pressure could compress much of the planet's interior carbon directly into crystalline diamond, a genuinely speculative but mathematically consistent possibility for at least one confirmed exoplanet, 55 Cancri e, whose unusually low measured density and carbon-rich host star chemistry have made the diamond interior hypothesis a serious, if still unconfirmed, subject of ongoing modeling. As of the most recent published counts, astronomers have formally confirmed more than 5,800 exoplanets across more than 4,300 planetary systems, a number that continues climbing steadily as new surveys and increasingly sensitive instruments come online. And yet this entire confirmed catalog, astronomers are quick to point out, likely represents only a small fraction of the galaxy's true total planetary population, since current detection methods remain heavily biased toward large planets orbiting close to their stars, precisely the configurations easiest to detect through both the transit and radial velocity methods, meaning an enormous number of smaller, more distant, and potentially more Earth-like worlds almost certainly remain entirely undiscovered, waiting for a future generation of telescopes with the sensitivity to finally find them. The very first exoplanet atmosphere ever directly detected belonged to HD 209,458b, a hot Jupiter roughly 150 light-years away, nicknamed Osiris, where a 2001 Hubble Space Telescope observation confirmed the presence of sodium in the planet's upper atmosphere, and follow-up observations published in 2003 revealed something considerably stranger. The planet is actively losing its atmosphere to space, with hydrogen streaming off it fast enough to form a comet-like tail roughly 200,000 kilometers long, trailing behind the planet as it orbits its star at a distance of just 7 million kilometers, close enough that intense stellar radiation is slowly but steadily stripping the planet's gaseous envelope away entirely. Current models estimate HD 209,458b is losing mass at a rate of roughly 10,000 tons per second. And while that sounds catastrophic, astronomers calculate the planet's total mass is large enough that the process would take many times longer than the current age of the universe to fully evaporate it, making Osiris less an imminent disaster and more a genuinely useful natural laboratory for studying exactly how atmospheric escape works on close-orbiting worlds. A separate detection technique, called direct imaging, in which astronomers attempt to photograph an exoplanet's own light directly, rather than inferring its presence through a star's dimming or wobble, achieved its first genuinely convincing multi-planet result in 2008, when a research team using the Keck and Gemini observatories in Hawaii published images of 3, and shortly afterward a confirmed 4th, planets orbiting the young star HR 8799, roughly 129 light-years away, each planet several times the mass of Jupiter and orbiting at distances considerably farther from their star than any planet in our own solar system orbits the Sun, because the HR 8799 system is only about 30 million years old, astronomically speaking still cooling down from its own formation. Its planets remain warm enough to glow faintly in infrared light on their own, a narrow observational window that makes direct imaging dramatically harder around older, cooler planetary systems like our own, and one reason the technique has so far confirmed only a small handful of systems compared to the thousands of planets found through transits and radial velocity measurements. Among rocky, potentially habitable candidates discovered outside the TRAPPIST-1 system, LHS 1140b, announced in 2017 and orbiting a red dwarf star roughly 49 light-years away, has drawn particular scientific interest specifically because its estimated density suggests a rocky, iron-rich composition roughly 1.7 times Earth's radius, sitting comfortably within its star's habitable zone, and because, unlike many red dwarf planets discovered nearby, its host star shows a comparatively calm flare history, reducing at least one of the major habitability concerns that complicate the Proxima Centauri and TRAPPIST-1 cases discussed earlier in this chapter. James Webb Space Telescope observations of LHS 1140b remain ongoing as of the most recent published mission schedule, with astronomers specifically hoping to determine whether the planet retains any atmosphere at all, a question that, once answered, will meaningfully sharpen the still fairly wide statistical uncertainty around how common genuinely atmosphere-retaining rocky worlds actually are around the galaxy's most common type of star. Beyond planets themselves, astronomers have also begun searching for exomoons, satellites orbiting planets around other stars, and the single most closely examined candidate, reported in 2017 and studied further in IAT-10 by astronomers David Kipping and Alex Tichy, involves a large Neptune-sized moon apparently orbiting the gas giant Kepler 1625b, itself orbiting a sun-like star roughly 8,200 light-years away. The signal was detected through extremely subtle secondary dips and timing irregularities in the planet's own transit light curve, precisely the kind of faint effect a large orbiting moon would be expected to produce. But the candidate has never received broad scientific confirmation, and a separate reanalysis published in 2019, using different statistical assumptions, found no significant evidence for a moon at all, leaving Kepler 1625b, as the candidate is provisionally designated, in the same genuinely unresolved category as several other exomoon claims made since, none of which current telescope technology has yet been able to confirm or definitively rule out. For all the effort astronomers have poured into studying distant galaxies, quasars, and the largest structures in the observable universe, our own home galaxy, the one we're physically embedded within, and can never step outside of to observe from a genuinely external vantage point, still holds a genuinely surprising number of basic structural questions that remain only partially resolved. A reminder that proximity doesn't always translate into complete understanding. The Milky Way's overall spiral structure presents astronomers with a puzzle known, somewhat informally, as the winding problem. Basic orbital mechanics dictates that stars closer to a spiral galaxy's center complete their orbits considerably faster than stars farther out, meaning that if a galaxy's spiral arms were simply made of the same fixed population of stars rotating together, differential rotation should have wound the arms into a tight, indistinct spiral within just a few 100 million years, a small fraction of the Milky Way's roughly 13 billion-year age, since spiral arms clearly remain visible and well-defined across essentially every spiral galaxy astronomers have ever observed, including our own. The currently favored explanation, called density wave theory, proposes that spiral arms aren't fixed collections of the same stars at all, but rather slow-moving waves of gravitational compression passing through the galactic disk, triggering new star formation as gas clouds pass through the wave and temporarily brighten, with individual stars constantly entering and exiting the arm pattern as they orbit, much the way a traffic jam on a highway remains a persistent, visible pattern, even though the specific cars caught within it are constantly changing. This density wave explanation, while broadly accepted, still leaves open considerable debate about precisely what triggers and sustains the wave pattern in the first place, and competing models involving stochastic, self-propagating star formation continue to be actively developed and tested against observational data. At the very center of the Milky Way sits Sagittarius A, the supermassive black hole whose direct image, captured by the Event Horizon Telescope, has already been covered in an earlier installment of this series, but the environment immediately surrounding it holds its own separate and genuinely fascinating puzzle worth exploring here in full. A cluster of stars, collectively known as the S-stars, orbit Sagittarius A at extraordinarily close range, and the most closely tracked of them, a star designated S2, completes a full orbit in just under 16 years, reaching speeds of roughly 7,650 kilometers per second, nearly 2.6% of the speed of light at its closest approach to the black hole. Continuous tracking of S2's orbit since the early 1990s, conducted by two independent research teams using telescopes in Chile and Hawaii, provided astronomers with one of the most precise confirmations of general relativity ever obtained outside our own solar system, directly observing both gravitational redshift and a measurable precession in S2's orbital path, a Mercury-like effect, but occurring at a scale and gravitational intensity that Einstein himself never could have directly tested. What remains genuinely puzzling is how young, massive stars like several of the S-stars manage to form in the first place so close to a supermassive black hole's immensely disruptive tidal forces, an environment standard star formation theory suggests should make normal stellar birth all but impossible, a contradiction sometimes called the paradox of youth that continues to drive competing formation models involving either stars forming considerably farther away and later migrating inward, or unusual, still poorly understood formation processes unique to this extreme gravitational environment. The Milky Way's broader structural history received a genuinely significant revision in 2018, when data from the European Space Agency's Gaia satellite, the same mission responsible for the precision stellar mapping discussed in the first installment of this series, revealed clear evidence of an ancient galactic merger, now called the Gaia Sausage-Enceladus event, in which a smaller galaxy estimated at roughly the mass of one of the Milky Way's current large satellite galaxies collided with and was absorbed into our own galaxy approximately 8 to 11 billion years ago. The merger left a distinctive, sausage-shaped pattern in the orbital motions of a large population of ancient stars still identifiable within the Milky Way's halo. Today, a kind of fossil record hidden in plain sight within our own galaxy's stellar population, and researchers studying this ancient collision believe it played a genuinely significant role in shaping the Milky Way's early structural evolution, including possibly triggering a substantial early burst of star formation. Though the precise details of exactly how disruptive this ancient merger was to the galaxy's developing disk structure remain an active subject of ongoing simulation and debate. The Milky Way's own long-term future holds a genuinely dramatic and, for once in tonight's video, fairly well-established outcome: a collision with the Andromeda Galaxy, our nearest large galactic neighbor, currently approaching us at roughly 110 kilometers per second. Precise measurements of Andromeda's sideways motion, published by a research team using Hubble Space Telescope data in 2012, confirmed the two galaxies are on a direct collision course with current models, projecting the two galaxies will begin merging in roughly 4 to 4.5 billion years, a process that will unfold over hundreds of millions of years rather than happening instantaneously, given the vast distances separating individual stars within each galaxy, meaning direct star-to-star collisions during the merger itself are expected to be exceedingly rare, even as both galaxies' overall structures are gradually and dramatically reshaped into what astronomers have informally nicknamed Milky Way, a single, larger elliptical galaxy formed from the combination of both. A genuinely puzzling recent discovery involves a specific class of star found unexpectedly close to the galactic center called hypervelocity stars, moving fast enough, in some documented cases exceeding 1,000 kilometers per second, to eventually escape the Milky Way's gravitational pull entirely. The leading explanation for how these stars achieve such extreme velocities involves a close gravitational interaction with Sagittarius A itself, in which a binary star system, passing too close to the supermassive black hole, has one member captured into a tight orbit, while its companion is flung outward at extraordinary speed, a mechanism first proposed theoretically in 1988 by astrophysicist Jack Hills, and subsequently confirmed observationally beginning in 2005, when the first genuine hypervelocity star candidate was identified. Dozens of confirmed hypervelocity stars have since been catalogued, and studying their specific trajectories has become, somewhat unexpectedly, a genuinely useful indirect tool for mapping the distribution of dark matter throughout the Milky Way's outer halo, since the precise paths these extraordinarily fast stars follow as they escape the galaxy are shaped directly by the total gravitational mass, dark matter included, that they pass through along the way. The Milky Way's own total mass, a seemingly basic property for any object astronomers have studied as intensively as our own galaxy, remains, somewhat surprisingly, only approximately known rather than precisely measured, with different measurement techniques, including the motion of distant satellite galaxies, the dynamics of individual hypervelocity stars discussed above, and the Gaia satellite's precise stellar motion catalog, producing estimates that still vary by nearly a factor of 2, ranging from roughly 500 billion to more than 1 trillion times the mass of the Sun, once dark matter is included in the total. This persistent measurement uncertainty for an object astronomers can study in vastly more direct detail than any external galaxy ever could be studied, illustrates a genuinely important and somewhat humbling point that recurs throughout tonight's video. Proximity offers real advantages for detailed study, but it does not on its own guarantee that even the most basic properties of an object are already fully and precisely pinned down. Directly above and below the Milky Way's central plane sit two enormous, roughly symmetrical structures called the Fermi bubbles, giant lobes of gamma-ray emitting gas, first identified in 2010 using data from NASA's Fermi Gamma-Ray Space Telescope, each extending roughly 25,000 light-years out from the galactic center, together spanning more than half the visible sky when viewed in gamma rays from Earth. The bubbles' sharp, well-defined edges suggest they were produced by a single, relatively short and violent injection of energy from the galactic center, rather than a slow, continuous process, and the two leading competing explanations: a burst of star formation activity roughly 6 to 9 million years ago, or a comparatively sudden episode of active feeding by Sagittarius A itself, remain genuinely unresolved, with different lines of evidence, including the precise chemical composition of gas at the bubble's edges, offering only partial and occasionally conflicting support for either scenario. A separate and considerably more recent puzzle concerns Omega Centauri, the Milky Way's largest and brightest globular cluster, containing roughly 10 million stars packed into a region just 150 light-years across, visible to the naked eye from the southern hemisphere. A 2024 study using more than 20 years of accumulated Hubble Space Telescope imaging identified 7 stars near the cluster's core moving fast enough that only a central concentration of mass, roughly 8,200 times the mass of the Sun, compressed into a space smaller than our own solar system, could plausibly explain their speeds, evidence strongly suggestive of an intermediate mass black hole, a category of object that would fill the long-debated size gap between stellar mass black holes and the supermassive black holes found at galactic centers. Some astronomers studying Omega Centauri's unusual internal chemistry have proposed the cluster may actually be the stripped-down core of a separate, considerably smaller galaxy that the Milky Way gravitationally captured and largely dismantled. Sometime in the ancient past, an idea the possible intermediate mass black hole would fit neatly, since such a core remnant might plausibly have retained the kind of central black hole, a genuine dwarf galaxy, but not an ordinary globular cluster, would be expected to carry. A further, still genuinely contested anomaly involves what astronomers call the galactic center excess, a surplus of gamma-ray photons detected emanating from the region immediately surrounding Sagittarius, first identified in data from the Fermi Gamma-Ray Space Telescope and reported in a series of papers beginning around 2009. The excess radiation's overall energy spectrum and spatial distribution turned out to match remarkably closely. What theoretical models predict should be produced by dark matter particles colliding and annihilating with each other near the unusually dense concentration of dark matter expected at a galaxy's center, generating brief excitement that it might represent the first indirect detection of dark matter's actual particle nature. Subsequent, more detailed analysis, published through the 2010s, complicated this initially promising interpretation considerably. Finding the excess emission's fine spatial structure looks statistically more consistent with a large previously uncatalogued population of faint, rapidly spinning millisecond center than with a smooth dark matter distribution. Leaving the galactic center. Excess in a genuinely unresolved state between two very different explanations, one mundane and astrophysical, the other a potential landmark discovery about the nature of dark matter itself. On September 14, 2015, at 5:51 in the morning Eastern Daylight Time, twin detectors belonging to the Interferometer Gravitational Wave Observatory, commonly abbreviated LIGO, located roughly 3,000 kilometers apart in Louisiana and Washington state, simultaneously registered an almost impossibly faint ripple in the fabric of spacetime itself, a signal lasting just 0.2 of a second that had been traveling toward Earth for 1.3 billion years, generated by the final catastrophic merger of two black holes, one roughly 36 times the mass of the Sun and the other roughly 29 times, into a single larger black hole, an event formally catalogued as GW150914, and representing the first direct detection of gravitational waves in the history of science, exactly a century after Albert Einstein's general theory of relativity had originally predicted their existence in 1915. The sheer physical precision required to make this detection possible is genuinely difficult to convey in ordinary terms, and it's worth sitting with directly, since it explains why gravitational wave astronomy took an entire century to become technically achievable after Einstein's original prediction. LIGO's detectors work by splitting a laser beam and sending each half down a separate 4-kilometer-long vacuum tunnel arranged in an L shape, then precisely measuring any difference in the time it takes each beam to travel down its tunnel and bounce back, a difference that a passing gravitational wave would produce by very slightly stretching space in one direction, while very slightly compressing it in the perpendicular direction. The actual distortion LIGO detected from the September 2015 merger amounted to a change in each 4-kilometer tunnel's length of roughly 1/10,000th of the width of a proton, a level of precision engineers achieved only after decades of dedicated technological development specifically aimed at isolating the detector from every conceivable source of ordinary vibration, from passing trucks to distant earthquakes, to the thermal jostling of individual atoms within the mirrors themselves. Rainer Weiss, Kip Thorne, and Barry Barish shared the 2017 Nobel Prize in Physics for their decades-long leadership of the LIGO project, and the discovery immediately opened an entirely new observational window onto the universe, one fundamentally different from every prior method of astronomy, which had relied exclusively on detecting some form of electromagnetic radiation, visible light, radio waves, X-rays, and so on. Gravitational waves instead directly detect the motion of mass itself, offering astronomers a genuinely independent way of observing violent cosmic events, including ones like black hole mergers that produce essentially no light at all and would otherwise remain permanently invisible to every conventional telescope ever built. In the decade since that first 2015 detection, LIGO, joined by the Italian Virgo detector and, more recently, the Japanese Kagra detector, has confirmed nearly 100 separate gravitational wave events, the overwhelming majority representing binary black hole mergers, revealing, almost as a side effect of the detection process itself, a population of stellar mass black holes considerably more massive and considerably more numerous than astronomers had previously inferred. from conventional electromagnetic observations alone, a genuinely significant revision to models of how massive stars die and what they leave behind, achieved not through any new telescope pointed at visible light, but through listening, in a very real sense, to space-time itself ringing. One particularly significant early puzzle emerged from the population of merging compact objects. LIGO detected, sometimes called the lower mass gap problem, a genuinely different and, in astrophysical terms, more immediately puzzling gap than the upper pair instability gap discussed elsewhere in stellar physics. Conventional stellar evolution theory had predicted a fairly clean dividing line between the heaviest known neutron stars, generally topping out at around 2.2 times the mass of the Sun before collapsing further, and the lightest known black holes, rarely found below about 5 solar masses, leaving the range in between largely empty in every populated component of compact objects astronomers had catalogued through traditional electromagnetic observations. When LIGO and Virgo detected a merger on August 14, 2019, catalogued as GW1D Wayward 4, involving a black hole of about 23 solar masses, merging with a considerably smaller companion object of roughly 2.6 solar masses. That smaller companion landed squarely inside the supposedly empty gap, and to date, no instrument has been able to determine with full confidence whether it was the lightest black hole ever measured or the heaviest neutron star ever measured, a genuine either-or ambiguity that current neutron star physics models struggle to comfortably accommodate on either side, and one that has prompted renewed theoretical work on precisely how dense ordinary neutron star matter can become before it must collapse the rest of the way into a black hole. Gravitational wave astronomy has also opened up an entirely independent method for measuring the universe's expansion rate, directly relevant to the Hubble tension puzzle discussed in the first installment of this series. When gravitational waves and conventional light from the same event, such as the 2017 neutron-star merger, already covered in that earlier chapter, can both be detected simultaneously, astronomers can use the gravitational wave signal itself to calculate the event's distance with remarkable independence from the traditional cosmic distance ladder entirely, a technique astronomers call using the event as a standard siren. This method, still limited by the relatively small number of events detected with both gravitational and electromagnetic signals has so far produced Hubble constant measurements broadly consistent with, though not yet precise enough to definitively favor either side of, the ongoing Hubble tension controversy, and astronomers widely expect that as detector sensitivity improves and the number of jointly observed events grows over the coming decade, standard siren measurements could eventually provide an entirely independent third method for resolving the Hubble tension question, a genuine and actively anticipated future contribution to one of cosmology's most persistent open puzzles. Looking toward the future of this young field, the European Space Agency's Laser Interferometer Space Antenna, commonly known as LISA, currently scheduled for launch in the mid-2030s, will place 3 spacecraft in a triangular formation, trailing Earth's orbit around the Sun, separated by roughly 2.5 million kilometers each, forming a gravitational wave detector vastly larger than anything achievable on Earth's surface and specifically sensitive to lower frequency gravitational waves than LIGO and Virgo can detect, including the mergers of the supermassive black holes discussed in an earlier installment of this series. Events. LISA's space-based design will, for the first time, allow astronomers to observe directly rather than only inferring through the pulsar timing background, methods covered previously, a genuinely significant future expansion of humanity's ability to listen to the universe's most violent gravitational events, still, as of tonight's most recent information, roughly a decade away from its first actual observations. a specific category of gravitational wave that no detector has ever yet confirmed, called a continuous gravitational wave, would come not from a sudden, one-time merger event, but from an isolated, rapidly spinning neutron star with a slight persistent asymmetry in its shape, a bump on its surface potentially just millimeters tall, generating a steady, unchanging gravitational signal for as long as the star keeps spinning, because such a signal would arrive continuously, rather than as a brief chirp. Searching for one requires comparing years of accumulated LIGO data against millions of possible combinations of spin rate and orientation, a computational search so demanding that the LIGO collaboration has relied partly on distributed volunteer computing projects to help process it. And despite searching known pulsars, including several with precisely measured spin rates, no continuous gravitational wave signal has yet been confirmed, a non-detection that has itself proven scientifically useful, since it places a strict upper limit on just how lumpy a neutron star's surface can possibly be, a constraint that feeds directly back into the same neutron star interior physics discussed elsewhere in tonight's video. A further genuinely significant test made possible by LIGO's detections involves what physicists call the black hole ringdown, the brief, fading pattern of vibration a newly merged black hole exhibits in the fractions of a second immediately after formation, similar in general concept to the way a struck bell rings briefly before settling into silence. General relativity's no-hair theorem predicts that a black hole's ring-down pattern should be determined entirely by just two numbers, its final mass and its spin, regardless of whatever asymmetric or complicated collision produced it, and analysis of the clearest LIGO ring-down signals detected to date, published by multiple independent research groups since 2019, has found the observed vibration patterns broadly consistent with this prediction, offering some of the most direct available evidence that black holes really do behave as the remarkably simple, information-erasing objects general relativity describes, even as physicists studying the ring-down data continue searching, so far without success, for any subtle deviation that might hint at physics beyond Einstein's original equations. General relativity also predicts a subtler, still entirely unconfirmed effect called gravitational wave memory, a permanent, lasting distortion in the fabric of spacetime that should remain behind, in principle detectable through a tiny but permanent shift in the distance between test masses, even after a gravitational wave itself has finished passing through and the more familiar oscillating chirp signal has faded away entirely. First predicted theoretically in the 1970s and refined considerably through the 1990s, the memory effect is expected to be roughly 20 times fainter than the main gravitational wave signal from the same event, well below the sensitivity of LIGO's current generation of detectors, even for the loudest mergers observed so far, and astronomers now generally expect that confirming it directly will require either a considerably more sensitive future ground-based detector or the accumulated statistical combination of many hundreds of individual merger events, making gravitational wave memory one of the more concretely anticipated, if not yet achieved, milestones for the still young field of gravitational wave astronomy. The next generation of ground-based gravitational wave detectors, currently in active planning, aims to push sensitivity roughly tenfold beyond LIGO's current capability. The Einstein Telescope, a proposed underground European facility arranged in a triangular configuration, with 10-kilometer arms, and Cosmic Explorer, a proposed American successor with arms stretching 40 kilometers, would together be sensitive enough to detect essentially every stellar mass black hole merger occurring anywhere in the observable universe, out to redshifts corresponding to the universe's very earliest generations of stars, rather than the comparatively local, present-day universe sample LIGO and Virgo currently detect. Both facilities remain in early planning, site selection stages as of the most recent published project updates, with construction not expected to begin before the early 2030s. But astronomers already anticipate that this next generation of detectors, operating alongside LISA's space-based observations, would finally provide close to a complete, unbroken gravitational wave census of the universe's entire merger history, from the earliest black holes formed after the first stars died to the most recent mergers, occurring in our own cosmic neighborhood today. Of all the concepts woven through tonight's video and through the entire field of physics more broadly, few remain as genuinely and persistently mysterious, despite their apparent familiarity, as time itself, a quantity every human being experiences directly and continuously, and that physicists still cannot fully explain at a fundamental level. The most basic unresolved puzzle involves what physicists call the arrow of time, the simple universal observation that time seems to flow in one direction only, from past to future, with cause reliably preceding effect and events like a dropped glass shattering but never spontaneously reassembling. The genuinely strange part, worth sitting with directly, is that nearly every fundamental equation in physics, from Newton's laws of motion to Einstein's general relativity to the core equations of quantum mechanics, works equally well running forward or backward in time, producing no mathematical preference whatsoever for one direction over the other. The one significant exception involves the second law of thermodynamics, which states that entropy, a measure of disorder, within a closed system, tends to increase over time, and the fact that our universe began roughly 13.8 billion years ago in an extraordinarily low entropy, highly ordered state gives entropy's steady increase since then a specific, consistent direction. To point in, a direction many physicists now believe is the actual underlying source of time's apparent one-way flow, though exactly why the universe began in such an improbably low entropy state in the first place remains, itself, a genuinely open cosmological question rather than a fully settled one. A separate and equally strange puzzle involves whether time, as most people intuitively experience it, a continuous, universally shared now flowing steadily forward, actually corresponds to anything physically real at all, or whether it's instead a kind of persistent cognitive illusion generated by how human brains process sequential information. Einstein's own special and general theories of relativity, both extensively and repeatedly confirmed through direct experiment, imply a considerably stranger picture, sometimes called the block universe or eternalism, in which past, present, and future all exist equally and permanently within a single four-dimensional structure of space-time, with the apparent flow of now representing merely a subjective, moment-by-moment slice through that structure, rather than any objective feature of reality moving through it. This interpretation is not, it's worth being clear, universally accepted among working physicists, and a smaller but genuinely serious minority continue to argue for an alternative view, sometimes called presentism, in which only the present moment genuinely exists in any meaningful physical sense, a debate that has persisted largely unresolved for more than a century, in part because the two positions currently make essentially identical experimental predictions, leaving the disagreement to sit closer to the territory of philosophy of physics than to anything a laboratory experiment could directly settle. What is considerably less philosophically contested, and instead extremely well experimentally confirmed, is that time genuinely does not pass at a fixed, universal rate, a direct and repeatedly verified consequence of Einstein's relativity called time dilation. Clocks moving at high speed relative to an observer run measurably slower than stationary clocks, and clocks positioned within a stronger gravitational field likewise run measurably slower than clocks farther from that same gravitational source, effects confirmed through numerous careful experiments, including the famous 1971 Hafele-Keating experiment, in which physicists flew extremely precise atomic clocks around the world aboard commercial airliners and measured a tiny but exactly predicted discrepancy compared to a matching reference clock left on the ground, confirming both the velocity-based and gravity-based components of Einstein's predictions simultaneously to within the experiment's own margin of error. This effect carries genuine, direct practical consequences for a piece of technology billions of people use every single day without ever thinking about the underlying physics involved. GPS satellites orbit Earth at an altitude of roughly 20,200 kilometers, moving at speeds of about 14,000 kilometers per hour, and experience two competing relativistic effects simultaneously. Their high orbital speed causes their onboard atomic clocks to run slightly slower than clocks on Earth's surface by about 7 microseconds per day, while their weaker gravitational field at that altitude, farther from Earth's mass than the surface, causes their clocks to run slightly faster, by about 45 microseconds per day, for a net effect of roughly 38 microseconds of clock gain per day once both relativistic factors are combined. If GPS engineers had not deliberately corrected for this precise combination of relativistic effects, the entire global positioning system would accumulate a position error of roughly 10 kilometers within just a single day, rendering the system essentially useless for navigation within hours, a genuinely striking, entirely practical, everyday confirmation that Einstein's 100-year-old equations describing the strange behavior of time are not merely abstract theoretical curiosities, but load-bearing components of infrastructure most people rely on dozens of times daily without ever realizing it. The so-called twin paradox, a specific thought experiment Einstein's relativity produces, offers one of the most genuinely disorienting confirmed consequences of time dilation, worth walking through directly. If one twin remains on Earth while the other travels at a significant fraction of the speed of light to a distant star and back, the traveling twin will, upon return, have genuinely aged less than the twin who stayed behind, not merely appeared to age less through some trick of observation, but actually experienced less elapsed time in an absolute physically real sense. This effect has been directly confirmed at a considerably smaller but still measurable scale through astronaut Scott Kelly's real 340-day mission aboard the International Space Station beginning in 2015, during which his identical twin brother, retired astronaut Mark Kelly, remained on Earth as part of a formal NASA twins study, with Scott returning to Earth measurably, if only by a small fraction of a second, younger than he would have been had he remained on the ground the entire time, a genuine, if vanishingly small, real-world demonstration of a paradox originally proposed as a purely theoretical exercise more than a century earlier. Perhaps the deepest and most genuinely unresolved question connected to time involves what happens to it at the quantum level, where physicists have found that time behaves in ways that resist easy reconciliation with either its relativistic treatment or its everyday intuitive meaning. In standard quantum mechanics, time is treated as an external fixed background parameter rather than as a genuine, physical quantity a system can be measured to have, in sharp contrast to how general relativity treats time as fully dynamic and inseparable from space itself, a fundamental incompatibility between physics' two most successful theories that lies at the very heart of the ongoing decades-long search for a complete theory of quantum gravity, a search that remains, as of tonight's most recent information, genuinely unresolved, and one directly connected to several of the deepest open questions covered elsewhere across tonight's video. This same tension produces what physicists studying quantum gravity call the problem of time in its most formal mathematical sense. When physicist Bryce DeWitt and John Wheeler worked out, in 1967, what the basic equation governing the entire universe's quantum state should look like, if general relativity and quantum mechanics were combined in the most straightforward possible way, the resulting equation, now called the Wheeler-DeWitt equation, contained no time variable at all, describing a universe that, at the most fundamental level the equation captures, simply does not change. Physicists have spent the decades since proposing various ways to recover the familiar, flowing sense of time from this fundamentally timeless underlying equation, most commonly by treating time as an emergent property that arises only when one part of the universe is used as an internal clock to measure changes. In the rest of it, an approach that remains mathematically workable but that has never achieved the kind of broad, settled consensus that would let physicists say the problem of time is genuinely solved rather than merely worked around. A related but far more experimentally grounded puzzle concerns how the human brain itself constructs the felt experience of now, a question neuroscientist Benjamin Libet investigated directly in a series of experiments published beginning in 1983, in which subjects were asked to note the exact moment they consciously decided to perform a simple hand movement while their brain activity was continuously monitored. Libet's results showed a measurable buildup of brain activity, called the readiness potential, beginning several hundred milliseconds before subjects reported becoming consciously aware of having made the decision at all, a finding that has generated more than 4 decades of continued debate among neuroscientists and philosophers over what it actually implies about free will and the brain's own internal timeline, since it suggests the felt, subjective sense of a decision's exact timing may itself be a kind of after-the-fact construction, rather than a direct real-time readout of when the decision genuinely occurred. A considerably more speculative but genuinely serious thought experiment connected to time's arrow and the universe's long-term entropy increase involves what physicists have nicknamed the Boltzmann brain problem, named after 19th-century physicist Ludwig Boltzmann, whose own statistical work on entropy first raised a version of the underlying puzzle. If the universe continues expanding indefinitely and entropy keeps rising toward an eventual state of maximum disorder, standard statistical reasoning suggests that, over sufficiently vast stretches of time, random quantum fluctuations within that near equilibrium void should occasionally, purely by chance, assemble a fully self-aware, momentarily conscious brain complete with false memories of an entire life never actually lived. And, troublingly, basic statistical calculations suggest such a randomly fluctuated brain should vastly outnumber every genuine, ordinarily evolved conscious observer that a universe like ours could ever produce across its entire history. Cosmologists take the Boltzmann brain problem seriously, not because anyone believes it describes our own actual situation, but because a cosmological model that predicts most conscious observers should be random statistical fluctuations rather than the product of ordinary stellar and biological evolution is generally treated as a model that has gone wrong somewhere, making the Boltzmann brain scenario a genuinely useful diagnostic tool physicists use to test and constrain competing proposals for the universe's ultimate long-term fate. At this very moment, roughly 100 trillion neutrinos, tiny, nearly massless subatomic particles produced primarily by nuclear reactions in the Sun, are passing directly through your body every single second, and passing through the entire planet Earth beneath you with almost the same ease, since neutrinos interact so weakly with ordinary matter that the overwhelming majority pass through solid rock, metal, and living tissue alike, without ever once colliding with a single atom, a property that has earned them their popular nickname among physicists, ghost particles. The IceCube Neutrino Observatory, an extraordinary detector built directly into the ice at the South Pole, buried between 1.45 and 2.45 kilometers beneath the surface, and encompassing a full cubic kilometer of ultra-clear Antarctic ice, represents one of the most genuinely unusual scientific instruments ever constructed, using more than 1,000 light sensors called photomultiplier tubes frozen permanently into the ice itself to detect the extraordinarily rare flashes of light produced when a high-energy neutrino occasionally does interact with an ice molecule. IceCube, which became fully operational in December 2010 after a construction process spanning multiple Antarctic summer seasons, was specifically built to detect the rarest and most energetic neutrinos in the universe, those originating from outside our own solar system entirely, and in September 2017, it achieved a genuine landmark, detecting a single extraordinarily high-energy neutrino that could be traced back, through follow-up observations from telescopes around the world, to a specific flaring blazar, a type of galaxy with an active supermassive black hole beaming a jet of particles almost directly toward Earth, roughly 3.7 billion light-years away, providing one of the first direct pieces of evidence connecting a specific astrophysical source to the mysterious, extremely high-energy cosmic neutrinos. IceCube had been detecting in small but steady numbers for years without being able to trace their origin. Neutrinos come in three known types, or flavors, called electron, muon, and tau neutrinos, and the discovery that they can spontaneously transform between these types during flight, a phenomenon called neutrino oscillation, proved conclusively that neutrinos possess a tiny but genuinely non-zero mass, a finding that itself generated an entirely new and still genuinely unresolved puzzle physicists call the neutrino mass hierarchy problem. While oscillation experiments can precisely measure the differences between the three neutrino types' masses, they cannot, using currently available experimental techniques, determine the actual ordering of those masses, meaning physicists genuinely don't yet know whether the neutrino type with the smallest mass sits at the bottom of the hierarchy, or, in an alternative arrangement called the inverted hierarchy, whether it instead sits at the top, a distinction that carries real consequences for several deeper, open questions in particle physics, and won several major current and planned experiments, including the Deep Underground Neutrino Experiment, currently under construction in the United States, are specifically designed to finally resolve. A separate and considerably more exotic open question involves whether a fourth type of neutrino, called a sterile neutrino, might exist alongside the three confirmed flavors, a hypothetical particle that would interact with ordinary matter, even more weakly than conventional neutrinos already do, potentially only through gravity, making it, if real, an entirely new and genuinely compelling dark matter candidate distinct from the WIMPs and axions discussed in the first installment of this series. Several experimental anomalies observed since the 1990s, including unexpected results from the LSND experiment at Los Alamos National Laboratory and later the Mini-Boon experiment, have hinted at the possible existence of sterile neutrinos, though subsequent, more precise experiments, including the Micro-Boon experiment, which published results in 2021, have failed to confirm these earlier hints under more careful and more statistically rigorous experimental conditions, leaving the sterile neutrino hypothesis in a genuinely uncertain state, neither confidently confirmed nor entirely ruled out. A frustrating but scientifically honest position. Several major ongoing and planned neutrino experiments continue actively working to resolve one way or the other. Perhaps the most fundamental unanswered question connected to neutrinos involves whether they are what physicists call Majorana particles, meaning each neutrino would be its own antiparticle, a genuinely strange possibility unique among all known fundamental particles, and one with direct, significant implications for understanding the antimatter puzzle discussed in a later chapter of tonight's video. If neutrinos genuinely are Majorana particles, a specific and exceedingly rare nuclear decay process called neutrinoless double beta decay should theoretically occur, and several major international experiments, including Gerda and its successor Legend in Italy, along with the Camlin-Zen experiment in Japan, have spent the past 2 decades searching for direct evidence of this specific decay process, using extraordinarily sensitive detectors shielded deep underground, specifically to block out interfering background radiation. As of the most recent published results, no experiment has yet detected confirmed neutrinoless double beta decay, meaning the Majorana question remains formally open, though each successive generation of increasingly sensitive detectors has meaningfully narrowed the range of possible neutrino masses and decay rates consistent with a non-detection, gradually closing in on either a genuine discovery or an increasingly confident exclusion as detector technology continues to improve. Beyond the neutrinos produced by the Sun and by high-energy astrophysical sources like the Blazar ice cube detected, cosmologists predict the existence of an entirely separate and vastly more numerous population called the cosmic neutrino background, ghostly relic particles released just 1 second after the Big Bang itself, considerably earlier than the cosmic microwave background's own release, 380,000 years later, meaning a direct detection of these primordial neutrinos would offer astronomers an unprecedented direct look at the universe's very first moments, far earlier than any other observational method currently available. Despite decades of theoretical interest, no experiment has ever directly detected the cosmic neutrino background. Since these particular relic neutrinos have cooled to such extraordinarily low energies over the universe's 13.8 billion-year history that they fall well below the sensitivity threshold of every currently existing detector, including IceCube, leaving their existence supported only indirectly through the way their calculated presence and energy density improves the accuracy of independent cosmological models like the ones used to interpret the cosmic microwave background, an indirect confirmation physicists generally consider strong, but that leaves direct detection of these earliest possible cosmic messengers as one of neutrino physics's most significant remaining open frontiers. The neutrino oscillation phenomenon discussed above was first confirmed not through a laboratory experiment, but through a genuine, decades-long astronomical mystery. Beginning in 1968, chemist Raymond Davis Jr. operated a detector filled with 615 tons of cleaning fluid inside the Homestake mine in South Dakota, specifically to count neutrinos streaming from the Sun. And for more than 2 decades his results consistently found only about a third of the solar neutrinos that the leading theoretical solar model, developed by physicist John Bacall, predicted should be arriving, a persistent shortfall that became known as the solar neutrino problem, and that some physicists initially suspected pointed to a flaw in scientists' understanding of the Sun's own internal fusion processes, rather than in neutrino physics itself. The mystery was finally resolved in 1998 when Japan's Super Kamiokande detector, a vast tank holding 50,000 tons of ultra-pure water buried a kilometer underground, provided the first strong experimental evidence that neutrinos genuinely do oscillate between flavors in flight, meaning Davis's detector, tuned to catch only one specific neutrino flavor, had simply been missing the 2/3 that had transformed into other types before arriving, a resolution that earned Super Kamiokande's lead researcher, Takaki Kajita, a share of the 2015 Nobel Prize in Physics, and that retroactively vindicated both Davis's careful decades-long measurements and Bacall's original solar model simultaneously. Not every neutrino reaching a detector originates from the Sun or from deep space at all. A meaningful fraction come from directly beneath our feet, produced by the natural radioactive decay of uranium, thorium, and potassium isotopes embedded within Earth's own crust and mantle, a category physicists call geoneutrinos, first directly detected in 2005 by the Camland experiment in Japan. Because geoneutrinos are produced by exactly the same radioactive decay processes responsible for generating a significant share of Earth's total internal heat, measuring there Flux offers geophysicists a genuinely direct way of testing competing models of the planet's deep internal composition and heat budget, and combined results from Camland and the Borexino experiment in Italy, published through the 2010s, have confirmed that radioactive decay likely accounts for roughly half of Earth's total internal heat output, with the remaining portion attributed to residual primordial heat left over from the planet's original violent formation, a genuine split that remains only approximately, rather than precisely, constrained, and one geoneutrino detectors continue refining with each additional year of accumulated data. Neutrinos have also begun to complicate the entirely separate search for dark matter discussed in the first installment of this series through a subtle problem physicists call the neutrino floor. Experiments like Xenont, buried deep underground in Italy specifically to search for the faint, rare recoil, signal a dark matter particle would leave behind after striking an ordinary atomic nucleus, have grown so sensitive over the past decade that they've begun detecting a genuine background signal from solar and atmospheric neutrinos undergoing the same kind of rare nuclear recoil interaction, a background that, past a certain sensitivity threshold, becomes essentially indistinguishable from the exact signal a real dark matter particle would produce. As of the most recent published results, several leading direct detection dark matter experiments have already begun brushing up against this neutrino floor for specific candidate particle masses, meaning any future dark matter claim in that mass range will need to somehow statistically separate a genuine dark matter signal from an irreducible neutrino background, a specific and genuinely difficult new experimental challenge that didn't meaningfully exist a decade ago, and that current detector designs are only beginning to grapple with directly. On the night of October 15, 1991, a detector in the Utah desert called the Fly's Eye recorded the arrival of a single subatomic particle carrying an energy of approximately 3 × 10 to the 20th power electron volts, an amount of energy comparable to a well-thrown baseball packed entirely into one single subatomic particle traveling at extraordinarily close to the speed of light, an event so far beyond anything physicists had previously recorded that it earned the informal nickname the "Oh my God" particle, a name that has stuck in both scientific and popular discussion of the event ever since. Cosmic rays, the broader category of high-energy particles this event belongs to, are not, despite the name, actually rays of light at all, but rather charged subatomic particles, primarily protons along with a smaller fraction of heavier atomic nuclei, arriving at Earth from deep space at velocities and energies that at the very highest end of the observed spectrum remain genuinely unexplained by any confirmed astrophysical process. Lower energy cosmic rays, making up the overwhelming majority of the total flux Earth constantly receives, are reasonably well understood, generally attributed to supernova remnants, the expanding shock waves left behind after massive stellar deaths, which are known to be capable of accelerating charged particles to significant fractions of the speed of light through a well-understood process called diffusive shock acceleration. The very highest energy cosmic rays, the ultra-high energy category the "Oh my God" particle belongs to, pose a considerably more serious problem, since no confirmed astrophysical source, not even the most extreme known objects, including supermassive black holes and gamma-ray bursts, has ever been definitively linked to producing particles carrying quite this much individual energy, leaving their true origin among the most significant open questions in all of modern astroparticle physics. Compounding the mystery, directly, theoretical physicists Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin independently calculated in 1966 that cosmic ray protons traveling across truly vast cosmic distances should lose energy through interactions with the cosmic microwave background radiation discussed in the first installment of this series, a theoretical energy ceiling now called the GZK cutoff, above which protons originating from sources more than about 160 million light-years away should not be able to retain their full energy by the time they reach Earth's detectors. Yet the oh my god particle and a small but genuinely confirmed handful of comparably extreme events detected since appear to exceed this theoretical limit, meaning either their true sources lie unexpectedly close to our own galaxy by cosmic standards, a genuinely puzzling requirement, given how few nearby astrophysical objects seem energetic enough to produce particles this extreme in the first place, or in a considerably more speculative alternative some theorists have proposed, that some entirely new and currently unknown physical process is responsible for their production. A possibility that remains formally unconfirmed, but that continues to attract serious ongoing theoretical attention. The Pierre Auger Observatory, spanning an enormous 3,000 square kilometers of remote Argentine countryside, roughly the size of the state of Rhode Island, represents humanity's largest and most sophisticated attempt to definitively resolve this mystery, using more than 1,600 individual particle detectors spread across the observatory's vast footprint, working in combination with dedicated telescopes that observe the faint ultraviolet fluorescence produced when an ultra-high energy cosmic ray strikes the upper atmosphere and triggers a cascading shower of secondary particles. Data published by the Pierre Auger Observatory in 2017, drawing on more than a decade of accumulated observations, revealed a subtle but statistically significant directional pattern in where the highest energy cosmic rays actually originate from, showing a modest excess of events arriving from a broad region of sky roughly corresponding to the general direction of nearby extragalactic space, rather than from within our own galaxy. Evidence supporting an extragalactic origin for at least the most extreme cosmic rays, though still without pinpointing any single specific confirmed source object precisely enough to fully close the case. A further layer of genuine mystery involves cosmic rays at the opposite end of the energy spectrum from the oh my god particle, specifically the puzzle of exactly what accelerates cosmic ray particles up to the highest energies confirmed to originate from within our own galaxy, sometimes called the key problem, referring to a distinctive bend in the overall cosmic ray energy spectrum, first identified in 1958, where the number of detected particles drops off more steeply above a specific energy threshold than below it. While supernova remnants are broadly accepted as the source of lower-energy galactic cosmic rays, the specific physical mechanism responsible for this particular spectral bend, and whether it marks the genuine upper limit of what supernova remnant acceleration can achieve, or instead reflects some entirely separate astrophysical process taking over at higher energies, remains an actively debated question among astroparticle physicists studying the detailed shape of the cosmic ray spectrum. Cosmic rays also carry genuine, practical relevance well beyond pure astrophysical curiosity, since their constant bombardment of Earth's upper atmosphere has been directly linked, through multiple independent lines of research, to a measurable background rate of genetic mutation across all life on the planet's surface, a contributing factor to evolution's overall pace that existed continuously for the entire multi-billion-year history of life on Earth, long before humans ever developed any instrument capable of detecting the particles responsible for it. Cosmic rays additionally pose a documented and genuinely significant practical challenge for modern space exploration specifically, since astronauts traveling beyond the protective shielding of Earth's magnetic field, including any future crewed mission to Mars, would face a meaningfully elevated lifetime cancer risk from prolonged cosmic ray exposure, a specific and well-quantified engineering challenge that continues to shape spacecraft radiation shielding design for every space agency currently planning missions beyond low Earth orbit. Even setting aside the extreme GZK-defying particles discussed above, astronomers have long struggled to identify enough confirmed galactic sources capable of accelerating cosmic rays up to what's called the PV range, 1,000,000,000,000 electron volts. The theoretical ceiling supernova remnant shock acceleration should be able to reach according to standard models. A class of hypothetical source physicists nicknamed pevatrons, well before any were confirmed to exist. The high-energy stereoscopic system, a gamma-ray observatory in Namibia, reported the first strong candidate in 2016, identifying gamma-ray emission consistent with PV-scale particle acceleration occurring in the immediate vicinity of Sagittarius A itself, and a considerably larger 2021 survey, conducted using China's Large High Altitude Air Shower Observatory, identified a dozen additional pevatron candidates scattered across the galactic plane, including several associated with young, actively forming star clusters rather than supernova remnants alone, a finding that has meaningfully broadened astronomers' working picture of where the galaxy's highest energy cosmic ray accelerators actually sit, even as the precise acceleration mechanism at several of these newly identified sites remains under active theoretical investigation rather than fully and conclusively explained. Cosmic rays have also produced one of the more unexpected practical applications in modern archaeology through a technique called muon tomography, which uses the steady natural rain of muons, secondary particles produced when cosmic rays strike Earth's upper atmosphere, to see inside large solid structures the same way an X-ray sees inside a human body, since muons pass more easily through empty space than through dense stone. In 2017, the International Scan Pyramids project, placing muon detectors inside and around Egypt's Great Pyramid of Khufu, identified a previously unknown void at least 30 meters long hidden above the pyramid's Grand Gallery, a finding published in the journal Nature and independently confirmed using 3 separate detection technologies, marking the first major internal structural discovery inside the Great Pyramid in more than a century, achieved not through any excavation or drilling, but simply by patiently counting the cosmic ray muons that happened to pass through several billion tons of ancient limestone on their way to a detector sitting quietly underneath it. The steady rain of cosmic rays reaching Earth is not, itself, perfectly constant over time, and ground-based detectors have long recorded sudden, temporary drops in cosmic ray intensity called Forbush decreases after physicist Scott Forbush, who first systematically documented them in 1937, typically lasting several days and coinciding closely with large eruptions of solar plasma called coronal mass ejections, whose expanding magnetic fields temporarily shield the inner solar system from a portion of the incoming galactic cosmic ray flux. A separate and considerably more contested hypothesis proposed by physicist Hendrik Svensmark beginning in the late 1990s suggests this same cosmic ray flux might influence Earth's cloud cover through incoming charged particles seeding the formation of tiny, atmospheric aerosols that can subsequently grow into cloud condensation nuclei, a mechanism that, if real, would mean the Sun's roughly 11-year activity cycle indirectly modulates Earth's cloud cover and, by extension, its climate. Laboratory experiments conducted at CERN, published beginning in 2011 under the Cloud Project, confirmed that cosmic rays can indeed measurably enhance aerosol nucleation under controlled conditions, but the majority of atmospheric scientists studying the question have found the resulting effect too small to meaningfully explain observed climate variation, leaving Svensmark's broader cosmic ray climate hypothesis a minority position within the field rather than one enjoying anything close to scientific consensus. According to the standard model of particle physics, one of the most thoroughly tested and successful theoretical frameworks in the entire history of science, the Big Bang should have produced exactly equal quantities of matter and its mirror image counterpart, antimatter, particles identical to their ordinary matter counterparts in every measurable respect except for carrying opposite electric charge. Whenever a particle of matter meets its corresponding antimatter particle, the two annihilate each other completely, converting their entire combined mass directly into pure energy. And if the early universe truly did contain exactly equal quantities of both, as the Standard Model predicts it should have, the two should have annihilated each other almost entirely within the universe's first fraction of a second, leaving behind nothing but a bath of pure radiant energy and no matter whatsoever, no stars, no planets, no galaxies, and self-evidently, no astronomers left billions of years later to wonder why any of it exists at all. This discrepancy, called the baryon asymmetry problem, ranks among the deepest and most consequential unsolved puzzles in all of modern physics precisely because its resolution is a direct logical prerequisite for the existence of literally everything we can observe, ourselves very much included. Some tiny, currently unexplained asymmetry favoring matter over antimatter, estimated at roughly 1 extra matter particle for every billion matter-antimatter pairs that existed in the universe's earliest moments, must have existed, allowing that small residual excess of ordinary matter to survive the universe's early annihilation era and go on to form every star, planet, and living creature that has ever existed, while the antimatter counterpart to that residual matter appears, based on every observation astronomers have ever made, to be almost entirely absent from the observable universe today. Physicists have identified one genuine, confirmed piece of the puzzle, called CP violation, a subtle asymmetry in how certain particle interactions behave differently under a combined reversal of electric charge and spatial orientation, first experimentally confirmed in 1964 by physicists James Cronin and Val Fitch, studying the decay of subatomic particles called kaons, a discovery that earned them the 1980 Nobel Prize in Physics. CP violation demonstrates that the laws of physics do, in fact, treat matter and antimatter very slightly differently under specific circumstances, providing a genuine theoretical mechanism through which a small matter-antimatter imbalance could have emerged during the universe's earliest moments. The serious remaining problem is one of scale. The amount of CP violation confirmed within the Standard Model through decades of careful measurement across kaons and, more recently, particles called B mesons, is many orders of magnitude too small to account for the actual matter-antimatter imbalance astronomers observe throughout the universe today, meaning some additional, currently unidentified source of CP violation, operating through physics beyond the Standard Model's current framework, almost certainly must exist, though no experiment has yet definitively identified what that additional source actually is. The Alpha Magnetic Spectrometer, commonly abbreviated AMS-2, installed aboard the International Space Station in May 2011 during one of the final Space Shuttle missions, represents humanity's most sophisticated ongoing search for naturally occurring antimatter anywhere in the observable universe, continuously scanning cosmic rays passing through its detector for any trace of heavier antimatter nuclei, particularly antihelium, whose detection in any meaningful quantity would strongly suggest the existence of entire antimatter stars or even antimatter galaxies somewhere in the cosmos, regions where the local matter-antimatter imbalance might have gone the opposite direction from our own. As of the most recent published results, spanning more than a decade of continuous data collection involving well over 100 billion detected cosmic ray events, AMS-2 has recorded a small handful of tentative antihelium candidate signals, though the collaboration has been notably appropriately cautious in interpreting these rare events, since even a single confirmed detection of genuine cosmic antihelium would represent one of the most significant discoveries in the entire history of physics, a claim the team continues working to either definitively confirm or rule out as instrumental background noise, rather than announcing prematurely. Laboratory production of antimatter, while genuinely achievable using powerful particle accelerators, remains an extraordinarily inefficient and expensive process, and CERN's dedicated antimatter factory, part of the same laboratory complex responsible for the Large Hadron Collider, has succeeded in producing and, in a genuinely remarkable technical achievement, first accomplished in 2010, trapping actual antihydrogen atoms, complete antimatter versions of the simplest element, for periods extending up to 16 minutes using specialized magnetic containment systems, since antimatter would instantaneously annihilate upon contact with any ordinary matter container wall. These trapped antihydrogen atoms have allowed physicists to conduct genuinely precise comparative measurements between matter and antimatter for the first time in history, including a landmark 2023 experiment that directly measured antihydrogen falling under gravity, confirming, to the considerable relief of most physicists who had expected exactly this result based on general relativity's predictions, that antimatter falls downward under gravity in essentially the same way ordinary matter does, definitively ruling out a small but genuinely serious minority hypothesis that antimatter might instead experience gravitational repulsion, a hypothesis that, had it been confirmed instead, would have required a fundamental rewriting of general relativity itself. The total quantity of antimatter humanity has ever successfully produced and studied across the entire history of particle physics remains almost unimaginably small, with CERN's own public estimates suggesting that if every antiproton ever produced across the laboratories' entire operational history were combined and completely annihilated with ordinary matter, the resulting energy release would be sufficient to power a single light bulb for only a few minutes, a genuinely striking illustration of both how extraordinarily difficult antimatter is to produce using current technology and, by direct extension, how correspondingly powerful even a comparatively small natural antimatter source somewhere in the cosmos would necessarily have to be if AMS-2 or a future successor experiment ever did manage to confirm one. Despite antimatter's extreme rarity and cost, one specific application has become a routine, everyday part of modern medicine: positron emission tomography, commonly abbreviated PET scanning, in which patients receive a small dose of a radioactive tracer that emits positrons, the antimatter counterpart to ordinary electrons, first developed into a practical clinical imaging tool during the 1970s. When an emitted positron encounters an ordinary electron inside the patient's body, the pair annihilates, releasing two gamma rays in exactly opposite directions, and a ring of detectors surrounding the patient uses the precise timing and angle of those paired gamma rays to reconstruct a detailed three-dimensional image of metabolic activity inside the body, a technique now performed on millions of patients annually for cancer diagnosis, cardiac assessment, and neurological research, making matter-antimatter annihilation the same fundamental process theorists still cannot fully explain the cosmic asymmetry of, a routine and thoroughly unremarkable fixture of hospitals worldwide. Theoretical physicists have proposed several specific mechanisms beyond simple CP violation that might explain how the universe's matter-antimatter imbalance actually arose, and one of the most actively studied, called leptogenesis, proposes that the asymmetry originated not among ordinary matter particles directly, but among an exotic, extremely heavy hypothetical particle called a right-handed neutrino, decaying asymmetrically in the universe's first fraction of a second in a way that would have produced slightly more matter-associated leptons than antimatter-associated ones, an imbalance that later physical processes could have transferred over into the ordinary matter-antimatter asymmetry astronomers observe today. Leptogenesis remains attractive to many theorists specifically because it connects neatly to the neutrino mass puzzle discussed earlier in tonight's video, but it requires physics at energy scales far beyond anything the Large Hadron Collider or any currently planned successor could ever directly probe, meaning the theory, however elegant, is likely to remain a mathematically consistent possibility rather than a directly tested explanation for the foreseeable future. A second, considerably older proposed mechanism, called electroweak baryogenesis, suggests the matter-antimatter asymmetry could instead have been generated during a specific, extremely brief phase transition in the early universe, roughly 1/10 billionth of a second after the Big Bang, when the unified electroweak force split apart into the separate electromagnetic and weak nuclear forces observed today. For electroweak baryogenesis to work as originally envisioned, this phase transition would need to have occurred abruptly, in the way water abruptly transitions to ice at its freezing point, rather than smoothly and gradually, since only an abrupt transition could have created the sharp, out-of-equilibrium conditions. The process requires and detailed standard model calculations completed through the 1990s and refined since have consistently found the actual electroweak transition was too smooth and gradual, given the specific measured mass of the Higgs boson confirmed at CERN in 2012 to generate anywhere near enough asymmetry on its own, meaning electroweak baryogenesis, in its simplest original form, is now considered by most particle physicists to require some additional new particle or force beyond the standard model in order to remain a viable explanation at all. Antimatter's genuine, real-world scarcity hasn't stopped it from occupying a persistent place in serious engineering speculation about future spacecraft propulsion, precisely because matter-antimatter annihilation converts essentially 100% of the reacting mass directly into usable energy, a theoretical efficiency thousands of times greater than even the most optimistic nuclear fission or fusion rocket designs could ever achieve. NASA-funded feasibility studies, conducted during the 1990s and periodically revisited since, including work by physicist Gerald Smith at Pennsylvania State University, calculated that a spacecraft carrying just a few milligrams of stored antimatter, reacted in a controlled manner with ordinary matter, could theoretically provide enough energy to meaningfully accelerate a probe toward a nearby star system within a single human lifetime, a performance no chemical or conventional nuclear propulsion system could plausibly match. The entire concept remains firmly theoretical rather than remotely close to practical, however constrained by exactly the same production bottleneck already discussed earlier in this chapter, since humanity's cumulative antimatter output across the entire history of particle physics amounts to a quantity too small to see, let alone store safely aboard a spacecraft, meaning antimatter propulsion functions today as a genuinely useful benchmark for what physically ideal propulsion could look like, rather than as an engineering roadmap any space agency currently expects to follow within the foreseeable future. The fundamental constants of physics, the specific numerical values governing the strength of gravity, electromagnetism, and the two nuclear forces, are generally treated by working physicists as genuinely fixed, unchanging numbers, the same today as they were in the universe's earliest moments, and the same here on Earth as they are in the most distant observable galaxy. A small number of persistent experimental anomalies accumulated across recent decades have raised genuine, still unresolved questions about whether that foundational assumption is entirely correct in every single case. The most statistically significant of these anomalies involves a specific property of the muon, a heavier cousin of the ordinary electron, called its magnetic moment, often referred to using the shorthand G2, pronounced G-2. Theoretical. Physicists can calculate, using the standard model's equations, an extraordinarily precise predicted value for exactly how a muon should behave when placed within a strong magnetic field, and in April 2021, the muon G2 experiment at Fermilab near Chicago announced measurement results that differed from this theoretical prediction by an amount statisticians describe as reaching 4.2 standard deviations, a level of statistical significance genuinely intriguing to physicists, though still falling short of the 5 standard deviation threshold. the field conventionally requires before declaring a discovery fully confirmed rather than merely suggestive. This specific discrepancy is genuinely significant precisely because the Standard Model's predicted value for the muon's magnetic moment stands as one of the most precisely calculated numbers in the entire history of physics, verified to 14 decimal places through decades of painstaking theoretical work, making even this small, persistent measured deviation a matter of considerable ongoing scientific interest, since if the discrepancy holds up under further scrutiny and additional data collection, it would represent genuine, direct evidence for entirely new physics beyond the Standard Model's current framework, but potentially connected to as yet undiscovered particles the Standard Model simply doesn't currently account for at all. A separate and considerably longer-running anomaly involves whether the fine structure constant, a fundamental number describing the intrinsic strength of electromagnetic interactions and traditionally denoted using the Greek letter alpha, might actually vary very slightly across cosmic space and time rather than remaining perfectly fixed everywhere and always as standard physics generally assumes. Beginning in 1999, astronomer John Webb and colleagues, analyzing the precise lengths of light absorbed by distant gas clouds as it passed through them on its way to Earth from extremely distant quasars, published findings suggesting the fine structure constant may have been very slightly different, by roughly 1 part in 100,000 in the universe's distant past, compared to its value measured in laboratories today. This finding has never achieved broad scientific consensus, and several subsequent independent research teams, using different telescopes and different analytical techniques, have reported conflicting results, some finding evidence supporting a genuine variation and others finding no statistically significant variation at all, leaving the question, more than 2 decades after Webb's original 1999 paper, still genuinely unresolved rather than either confirmed or definitively ruled out, a persistent and unusually long-running open controversy even by the standards of tonight's video. A now resolved but genuinely instructive historical anomaly worth including here involves the Pioneer anomaly, a small, unexplained, and consistently measured deceleration detected in the trajectories of NASA's Pioneer 10 and Pioneer 11 spacecraft, launched in 1972 and 1973 respectively, as they traveled outward through the solar system on their way toward interstellar space. For roughly 3 decades, this small but persistent anomalous deceleration, first formally documented in a 1998 scientific paper, generated genuine speculation among some physicists that it might represent a subtle failure of general relativity itself at very large distances from the Sun, a possibility that, had it been confirmed, would have carried genuinely enormous implications for cosmology. In 2012, a research team led by physicist Slava Turyshev definitively resolved the mystery through careful thermal modeling, demonstrating that the anomaly was caused entirely by the uneven asymmetric way heat radiated away from the spacecraft's own onboard plutonium power source, producing a tiny but genuinely real thrust effect in exactly the direction and magnitude needed to fully account for the observed deceleration, a satisfying and complete resolution that stands today as a genuinely useful cautionary case study in how even a rigorously confirmed and independently repeated anomaly can ultimately trace back to a subtle, mundane engineering effect rather than any genuinely new physics. A related and, as of the most recent published analysis, still not fully resolved puzzle involves what's called the flyby anomaly, a small but repeatedly measured unexpected change in the velocity of several spacecraft, including NASA's Galileo, NEAR, Cassini, and Rosetta missions, as they performed gravitational slingshot maneuvers past Earth on their way to their ultimate destinations elsewhere in the solar system, using Earth's own gravity to gain additional speed and adjust their trajectory. In several of these documented cases, spacecraft gained a tiny but measurable amount of additional velocity beyond what standard orbital mechanics predicted they should, discrepancies amounting to just a few millimeters per second. And while various proposed explanations have been offered over the years, including subtle atmospheric drag effects and possible errors in how the spacecraft's velocity was being measured in the first place, no single explanation has yet achieved the kind of definitive, broadly accepted confirmation the Pioneer anomaly eventually received, leaving the flyby anomaly as one of the smaller but genuinely still open entries in this chapter's broader catalog of measured discrepancies between prediction and observation. Perhaps the most conceptually significant question connected to all of these individual anomalies involves a considerably deeper theoretical puzzle called the fine-tuning problem specifically, as it applies to the fundamental constants, actual numerical values. Distinct from the broader multiverse-related fine-tuning discussion covered in the first installment of this series, physicists have found that several of the Standard Model's most basic input parameters, including the specific mass of the Higgs boson relative to other, vastly larger energy scales the theory also describes, require what physicists call an extraordinarily precise and, by most theoretical accounts, deeply uncomfortable degree of numerical cancellation between otherwise enormous underlying quantities in order to produce the small, specific values. These constants are actually observed to have a problem sometimes called the hierarchy problem. This unresolved theoretical tension has directly motivated several major proposed extensions to the Standard Model, including supersymmetry, discussed further in a later chapter of tonight's video, none of which have yet received the kind of direct experimental confirmation that would settle the underlying question definitively, leaving the precise numerical values of nature's own fundamental constants among the most persistently strange and persistently unexplained features of the entire physical universe. A separate anomaly, called the proton radius puzzle, emerged in 2010, when a research team led by physicist Randolph Pohl measured the physical size of a proton using an exotic form of hydrogen in which the orbiting electron is replaced with a muon, a considerably heavier particle that, because of its mass, orbits much closer to the proton and is correspondingly more sensitive to the proton's exact physical size. The resulting measurement came out about 4% smaller than the previously accepted proton radius established through decades of conventional measurements using ordinary hydrogen and electron scattering experiments, a discrepancy small in absolute terms but large enough, given how precisely both measurement techniques had independently been calibrated, to register as a statistically serious anomaly rather than simple experimental noise, prompting speculation that it might even point toward an undiscovered particle interacting differently with muons than with electrons. The puzzle was substantially resolved between 2017 and 2019, when new, more careful measurements using both electron-based and muon-based techniques converged on the smaller value, indicating the original electron-based measurements, not the laws of physics, had carried the error, though a small number of physicists have noted the episode as a useful reminder of how a genuine and statistically significant measured anomaly can persist for the better part of a decade before ultimately tracing back to experimental technique rather than new fundamental physics. Perhaps the most quietly embarrassing anomaly among the fundamental constants involves Big G, the gravitational constant governing the basic strength of gravity itself, first measured by physicist Henry Cavendish in 1798, and remarkably still known today to only about 1 part in 10,000, a precision thousands of times worse than nearly every other fundamental constant in physics, including the fine structure constant discussed earlier in this chapter, despite gravity being the force humans have studied for the longest continuous stretch of recorded history. Different independent research teams, using different experimental setups, including torsion balance experiments similar in basic design to Cavendish's original 1798 apparatus and modern atom interferometry techniques, have published measured values for G that disagree with each other by amounts well outside their own individually stated margins of error, a persistent spread. The National Institute of Standards and Technology's own metrology researchers have openly acknowledged remains unexplained, and one that has prompted genuine, still ongoing speculation about whether some unaccounted systematic measurement error, common to multiple experimental designs, or, in a considerably more speculative minority view, some genuinely new physics specific to gravity at laboratory scales, might be responsible for a discrepancy that more than 2 centuries of increasingly careful measurement has so far failed to fully resolve. One of the most closely watched recent anomalies among the fundamental constants briefly appeared, then largely dissolved, over the course of just 2 years. In April 2022, the CDF collaboration at Fermilab, analyzing data collected from the now-retired Tevatron particle collider over more than a decade, published a measurement of the W boson's mass, one of the specific particles responsible for carrying the weak nuclear force, that came in noticeably heavier than the Standard Model's precise predicted value, a discrepancy reported at a statistical significance of 7 standard deviations, comfortably past the 5 standard deviation threshold physicists conventionally require to call a result a confirmed discovery, briefly generating some of the most serious new physics speculation particle physics had seen in years. The excitement proved short-lived. In September 2023, the ATLAS collaboration at CERN's considerably newer and more precise Large Hadron Collider published its own independent W boson mass measurement, finding a value fully consistent with the Standard Model's original prediction and inconsistent with CDF's earlier result, and subsequent expert review of the CDF analysis identified several subtle methodological choices that plausibly explained the discrepancy, leaving the current expert consensus leaning toward the CDF measurement as an unresolved instrumental effect rather than evidence for new physics, though the broader particle physics community has, by its own general standards, not yet treated the question as fully and finally closed. Determining whether life exists anywhere beyond Earth has, over the past 2 decades, evolved from a largely philosophical question into a genuine, methodologically rigorous scientific discipline, one built around searching for specific, carefully defined chemical and physical signatures that life as we understand it would be expected to produce, and every single finding discussed in this chapter carries the same genuine, honest uncertainty that has defined so much of tonight's broader video. A biosignature, in the strict scientific sense astrobiologists use the term, refers to any substance, chemical imbalance, or physical pattern whose presence would be difficult to explain through purely non-biological or abiotic processes alone, and whose detection would therefore constitute meaningful, if not necessarily conclusive, evidence for the presence of life. Once upon a time, Earth's own atmosphere offers the clearest available example of what a strong biosignature actually looks like. Our planet's atmosphere maintains roughly 21% oxygen, a highly chemically reactive gas that would, without continuous biological replenishment through photosynthesis, react with surface minerals and disappear from the atmosphere entirely within just a few million years, meaning oxygen's simple ongoing presence in Earth's atmosphere is itself a direct, continuously renewed signature of active biological processes, a signature astronomers now specifically search for in the atmospheres of distant exoplanets using the same transmission spectroscopy technique discussed in an earlier chapter of tonight's video. One of the most closely watched and most genuinely contested recent biosignature claims involves Venus, our own solar system's nearest planetary neighbor, where a research team led by astronomer Jane Greaves announced in September 2020 the detection of phosphine gas within Venus's upper atmosphere, a chemical compound that, Earth, is produced almost exclusively through biological processes or specific industrial activity, with no well-established abiotic pathway capable of producing it in significant quantities under conditions resembling Venus's own harsh atmospheric chemistry. The announcement generated immediate, intense scientific interest and equally immediate scientific scrutiny, and several subsequent independent research teams, reanalyzing the same underlying radio telescope data using different statistical methods, reported considerably weaker or even entirely absent phosphine signals, while other researchers proposed several plausible abiotic explanations for how phosphine might form on Venus after all, including specific volcanic or unusual photochemical processes not previously considered likely under Venusian atmospheric conditions. As of the most recent published analyses, the Venus phosphine question remains genuinely unresolved, neither confidently confirmed as a biosignature nor definitively explained away through purely chemical processes, a case astrobiologists frequently cite as a useful, if occasionally frustrating, working example of exactly how rigorous, self-correcting, and appropriately cautious a genuine biosignature claim needs to be handled before the broader scientific community can reach any confident conclusion either way. The K218b finding, briefly introduced in an earlier chapter of tonight's video, deserves fuller treatment here as a second, considerably more recent biosignature case study. K218b, a sub-Neptune-sized exoplanet orbiting within the habitable zone of a red dwarf star roughly 124 light-years away, drew significant scientific attention in September 2023, when a research team using James Webb Space Telescope data reported a tentative detection of dimethyl sulfide, a chemical compound produced on Earth almost exclusively by marine phytoplankton and other living organisms within the planet's atmosphere. The research team itself, in a pattern of careful scientific caution that recurs throughout this entire chapter, explicitly emphasized that the detection sat at a statistical significance too low for confident confirmation, and that considerably more observation time would be required before the finding could be treated as anything beyond a genuinely interesting but firmly preliminary result. Caution that proved well justified when a separate 2024 analysis by an independent research team, re-examining the same underlying data using different atmospheric modeling assumptions, found the dimethyl sulfide signal considerably less statistically robust than the original announcement had suggested, leaving K218b's status, like Venus's phosphine before it, in a genuinely open and actively contested state rather than a settled scientific conclusion. Beyond searching for the direct chemical byproducts of microbial or plant-like life, a parallel research effort focuses specifically on technosignatures, detectable evidence of technology produced by an intelligent civilization distinct from the broader radio signal SETI search covered in the first installment of this series. One particularly creative proposed technosignature involves searching for unusual patterns of light dimming consistent with a Clark exobelt, a hypothetical dense ring of artificial satellites in geostationary orbit around a distant exoplanet. A technosignature concept named after science fiction author and satellite communications pioneer Arthur C. Clarke, whose 1945 paper first proposed the basic geostationary satellite concept humanity would go on to actually implement decades later. No confirmed Clark exobelt has ever been detected around any exoplanet studied so far, and the concept remains, for now, a theoretically well-developed but entirely unconfirmed proposed search strategy, one of several creative technosignature approaches astrobiologists have developed specifically to extend the search for intelligent life well beyond the traditional radio telescope-focused SETI methods discussed previously. Closer to home, the search for life has also focused considerable attention on Earth's own most extreme environments, studying organisms called extremophiles, life forms that thrive under conditions once assumed to be entirely incompatible with biology, including bacteria discovered living within deep-sea hydrothermal vents at temperatures exceeding 120 degrees Celsius, microorganisms found dormant but genuinely viable within ancient permafrost and even within salt crystals dated to hundreds of millions of years old, and tardigrades, microscopic multicellular animals capable of surviving direct exposure to the vacuum of space itself, confirmed through a genuine 2007 European Space Agency experiment that exposed live tardigrades to open space aboard an orbiting satellite and found a meaningful fraction survived the exposure and successfully reproduced afterward. These extremophile discoveries have directly and substantially expanded astrobiologists' working definition of where life might plausibly exist elsewhere in the solar system, lending genuine additional scientific weight to the habitability. Discussions surrounding Europa and Enceladus covered in the first installment of this series, since Earth's own extremophiles demonstrate, with direct physical evidence rather than mere theoretical speculation, that life can persist under conditions considerably more extreme than earlier generations of scientists had ever assumed possible. A final, genuinely unresolved and scientifically respectable question, worth closing this chapter with, involves panspermia, the hypothesis that life, or at least the basic chemical building blocks necessary for life, might be capable of traveling between planets, or even between star systems entirely, embedded within meteorites, comets, or other transported material, rather than necessarily originating independently on every single world where it's eventually found. Laboratory experiments have confirmed that certain hardy microorganisms and complex organic molecules can indeed survive the extreme heat, radiation, and mechanical shock of an actual meteorite impact under carefully controlled test conditions, lending genuine physical plausibility to the basic transport mechanism. Panspermia would require, though no direct evidence has ever confirmed, that life actually did originate somewhere else and subsequently travel to Earth, or that it has ever successfully traveled between any two worlds in either direction, leaving panspermia a scientifically serious, actively studied hypothesis that remains, like nearly everything else covered across tonight's entire video, a genuinely open question rather than a settled scientific fact. The single most famous and most thoroughly contested biosignature claim in the history of planetary science does not come from a distant exoplanet at all, but from a meteorite discovered in Antarctica's Allen Hills in 1984, later identified as a fragment of Mars ejected into space by an ancient impact and catalogued as ALH 84001. In August 1996, a NASA-led research team published findings in the journal Science identifying several features within the meteorite that they argued together constituted possible evidence of ancient Martian microbial life, including specific organic compounds called polycyclic aromatic hydrocarbons, distinctive mineral formations resembling structures produced by bacteria on Earth, and, most strikingly, tiny elongated structures visible only under electron microscopy that some team members believed resembled fossilized nanobacteria, an announcement significant enough that President Bill Clinton delivered brief, formal remarks about it from the White House lawn. Nearly every specific line of evidence in the original 1996 paper has since been challenged by independent research, with subsequent studies proposing plausible non-biological explanations for each feature individually, including purely geological processes for the mineral formations and contamination from Antarctic ice for at least some of the organic compounds, and the scientific consensus that has gradually emerged treats ALH 84001 not as confirmed evidence of past Martian life, but as a genuinely instructive cautionary case that helped establish the considerably stricter evidentiary standards astrobiologists now apply before any subsequent biosignature claim, including the Venus and K2-18b cases discussed earlier in this chapter, can be taken seriously by the broader scientific community. Every biosignature and technosignature case discussed across this chapter has been constrained by the same underlying limitation. No telescope currently operating was actually designed with direct imaging of small, rocky, Earth-like exoplanets as its primary purpose. NASA's proposed Habitable Worlds Observatory, formally recommended as the space agency's top priority large mission by the influential 2021 Astro 2020 Decadal Survey conducted by the National Academies of Sciences, is specifically intended to close this gap, designed to directly image dozens of potentially Earth-like rocky planets orbiting nearby Sun-like stars, and to analyze their atmospheres for oxygen, methane, and other candidate biosignatures using starlight blocking technology considerably more advanced than anything currently deployed. Currently targeting a launch sometime in the late 2030s, and still in the early conceptual design phase as of the most recent published. Mission updates. The Habitable Worlds Observatory represents the specific instrument astrobiologists most frequently cite as the mission that could finally move questions like the Venus phosphine and K2-18b dimethyl sulfide cases discussed above from genuinely uncertain single data points toward a broader, statistically meaningful survey of how common or how rare potential biosignatures actually are across a real sample of nearby, potentially habitable worlds. Running underneath every specific search effort covered in this chapter sits a broader and genuinely unresolved statistical disagreement among scientists themselves, sometimes framed as the rare Earth hypothesis, first laid out systematically in a 2000 book by paleontologist Peter Ward and astronomer Donald Brownlee. Their central argument holds that while simple microbial life may be relatively common throughout the universe, given how quickly it appeared on Earth's own surface once conditions allowed, complex multicellular life may require such a specific and improbable combination of factors: a large stabilizing moon, an active plate tectonic cycle, a particular history of protective gas giants, and a long, uninterrupted evolutionary stretch free of civilization-ending impacts, that Earth-like outcomes could be extraordinarily rare, even in a galaxy containing billions of potentially habitable planets. Critics of the rare Earth hypothesis, including several astrobiologists who point to the sheer number of confirmed rocky, potentially habitable exoplanets discussed earlier in this chapter, argue that Earth-specific formation history need not be unique for complex life to arise by some different but equally viable pathway elsewhere, and the disagreement remains. More than 2 decades after Ward and Brownlee's original argument, a genuine and unresolved scientific debate, rather than one side having accumulated enough evidence to settle the question either way. Beyond the dramatic stellar deaths and neutron stars already covered in the first installment of this series, the broader population of stars scattered across our galaxy includes an entire additional category of genuinely strange objects and unresolved stellar puzzles worth exploring in their own right, ranging from theoretical objects that may not exist at all to extremely common stars that turn out to hold their own quiet, persistent mysteries. Quark stars represent one of the most genuinely speculative entries in this entire chapter, a theoretical category of stellar remnant that would sit, in terms of density, somewhere between an ordinary neutron star and a black hole, formed under the hypothesis that at sufficiently extreme pressure, even the individual neutrons that make up a neutron star's interior might themselves break down into their most basic constituent particles, called quarks, forming an entirely new and even more compact state of matter called quark matter. No confirmed quark star has ever been directly observed, and the entire concept remains grounded purely in theoretical physics, though a small number of unusually compact objects detected through X-ray astronomy, including one candidate catalogued as RxJ 8856, 53754, and studied intensively since the late 1990s, have been proposed by some researchers as possible quark star candidates, specifically because their measured size appears somewhat smaller than standard neutron star models would predict for an object of their inferred mass, a genuinely intriguing but far from conclusive piece of indirect evidence that continues to generate active theoretical and observational research without yet producing a single confirmed detection. Pulsars, the rapidly spinning neutron stars first introduced in the first installment of this series, exhibit their own persistent and genuinely unresolved internal puzzle called pulsar glitches, sudden, small, and completely unpredictable increases in a pulsar's rotational speed, occurring against the pulsar's otherwise extraordinarily steady and gradual long-term slowdown. First observed in the Vela pulsar in 1969, just 2 years after pulsars themselves were originally discovered. These glitches are generally attributed to a sudden transfer of angular momentum between a neutron star's rigid outer crust and its considerably more fluid, superfluid interior, a kind of internal starquake analogous in some general respects to how Earth's own crust can suddenly shift during a seismic earthquake. The precise microphysical mechanism triggering any individual glitch event, and specifically why some pulsars glitch frequently, while others, spinning under seemingly comparable physical conditions, almost never do, remains an active area of theoretical modeling, one that offers physicists a genuinely unique natural laboratory for studying how matter behaves under densities and internal pressures no laboratory on Earth could ever hope to directly recreate or replicate. White dwarf stars, the compact stellar remnants left behind after a sun-like star exhausts its nuclear fuel and gently sheds its outer layers, hold their own significant unresolved puzzle directly connected to one of the standard candles astronomers rely on throughout tonight's and the first installment's discussions of cosmic distance measurement. Type, Supernovae, the specific class of stellar explosion used to measure the accelerating cosmic expansion discussed in the first installment of this series, are generally understood to occur when a white dwarf star, part of a binary system, accumulates enough additional mass, either by siphoning material from a companion star or through a direct collision with a second white dwarf, to cross a critical mass threshold called the Chandrasekhar limit, roughly 1.4 times the mass of the Sun, triggering a runaway thermonuclear explosion that destroys the star entirely. The genuine and still actively debated problem is that astronomers have not yet definitively determined which of these two competing formation pathways, gradual mass transfer from a companion star or a direct collision between two white dwarfs, actually produces the majority of observed type Ia supernovae, a distinction that matters considerably for cosmology specifically, since any subtle systematic difference between these two formation channels could, in principle, introduce a small but genuinely consequential bias into the very distance measurements astronomers have used for more than 2 decades to measure the universe's accelerating expansion in the first place. Brown dwarfs occupy a genuinely strange and only relatively recently well-characterized middle ground between the largest planets and the smallest true stars, objects massive enough to briefly fuse deuterium, a heavier isotope of hydrogen, early in their formation, but not massive enough to sustain the ordinary hydrogen fusion that powers genuine stars like our own Sun for their entire working lifetimes. The first confirmed brown dwarf, Gliese 229b, was directly imaged in 1995, and astronomers now estimate, based on surveys conducted since, that brown dwarfs may be nearly as numerous throughout the galaxy as ordinary hydrogen-fusing stars, an entire hidden population of dim cooling objects that emit so little light they remain extremely difficult to detect even at relatively close distances, meaning a meaningful and still only roughly estimated fraction of the Milky Way's total stellar mass population may consist of these genuinely in-between, objects quietly cooling in the dark for billions of years, largely uncounted in any simple census of the galaxy's visible stellar population. A final, genuinely unresolved stellar puzzle worth closing this chapter with involves the specific stars astronomers call blue stragglers, stars found within old star clusters that appear, based on their unusually blue color and high temperature, to be considerably younger than every other star in the same cluster, despite all the cluster stars having formed at essentially the same time from the same original collapsing gas cloud billions of years earlier. The leading explanation holds that blue stragglers form either through direct stellar collisions within a cluster's unusually densely packed core or through mass transfer from a close binary companion star, both processes that would effectively rejuvenate an aging star by supplying it with fresh hydrogen fuel, extending into parent stellar lifetime, and making it appear anomalously young compared to its actual formation age. Though determining precisely which specific formation mechanism produced any individual observed blue straggler remains, in most studied cases, a considerably harder observational problem than simply identifying that the anomaly exists in the first place. Among the purely theoretical entries in this chapter's catalog, few are stranger than the Thorne-Zitkow object, a hypothetical hybrid star first proposed in 1977 by physicists Kip Thorne and Anna Zitkow, in which a neutron star becomes gravitationally embedded directly inside the outer envelope of a much larger red supergiant star, most likely following a close binary collision, and continues orbiting deep within its companion's own churning interior rather than merging completely or being ejected. Because the neutron star's own intense gravity would trigger unusual nuclear fusion processes in the surrounding stellar material, theoretical models predict a Thorne-Zitkow object should produce a distinctive chemical fingerprint on its outer surface. Unusually high levels of specific elements, including lithium and rubidium, not normally found in such large quantities in an ordinary red supergiant's atmosphere. And in 2014, astronomers identified a star, catalogued as HV 2112 in the Small Magellanic Cloud, whose measured surface chemistry matched. Several of these predicted signatures closely enough to be proposed as the first plausible real-world candidate, a claim that subsequent more detailed spectroscopic analysis has treated with genuine caution rather than outright confirmation, leaving HV 2112's true nature formally unresolved. A separate and observationally better established stellar oddity involves so-called zombie stars, produced by a rare and genuinely counterintuitive category of stellar explosion called a Type IX supernova, a weaker, incomplete cousin of the standard Type EI explosion discussed earlier in this chapter, in which the thermonuclear runaway fails to fully disrupt the underlying white dwarf, leaving a battered but still intact stellar remnant behind, rather than destroying the star entirely. The best documented example, SN 2008HA, observed at only about 1% of a typical Type E type supernova's brightness, is now widely interpreted by astronomers as exactly this kind of partial explosion, and subsequent deep imaging of the location has identified a surviving, though visibly disturbed, stellar remnant consistent with a white dwarf that genuinely exploded, and against the ordinary expectation that such explosions are always fully destructive, kept on existing afterward. A final entry worth including in this catalog of stellar oddities is Contact Binary V1309 Scorpii, a system of two stars orbiting so closely they shared a single common envelope of gas, whose eventual violent merger astronomers had the rare privilege of watching unfold in advance. Amateur and professional observations accumulated between 2002 and 2008 tracked the binary's orbital period, steadily shortening as the two stars spiraled closer together, and when the stars finally merged in September 2008, the resulting outburst, formally classified as a luminous red nova, brightened the system by a factor of several thousand, an event whose entire progression, from stable binary to final merger, had been captured in unusually complete observational detail, specifically because archival survey data happened to already exist for the system before anyone knew it was heading toward collision. V339, Scorpius's well-documented merger, has since become the standard observational template astronomers use to identify other stellar systems currently spiraling toward a similar fate, including KIC 9,832,227, a contact binary predicted in a widely publicized 2017 announcement to merge and brighten dramatically sometime around 2022, a specific forecast that ultimately did not occur on schedule. Genuine miss that astronomers studying the case have treated less as a failure and more as a useful, humbling demonstration of just how difficult precisely timing a stellar merger years in advance actually remains. Returning briefly to the pulsar glitches introduced earlier in this chapter, the Vela pulsar, the very first pulsar ever observed to glitch back in 1969, remains more than 5 decades later the single most frequently glitching pulsar known, having undergone more than 20 confirmed glitch events since its discovery, each one a sudden, tiny speed-up in its otherwise remorselessly steady 89 millicent rotation. A particularly well-instrumented glitch captured in December 2016 by radio telescopes in Australia allowed astronomers to measure the star's rotational speed-up with unprecedented timing precision, confirming the event unfolded in under 12 seconds, a genuinely violent readjustment given that it involves a star roughly the mass of the Sun compressed into a sphere barely 20 kilometers across, and the sheer regularity with which Vela specifically continues to glitch roughly once every 3 years on average has made it the primary long-term natural laboratory astronomers rely on for testing competing theoretical models of neutron star interior physics, since no experiment conducted anywhere on Earth can recreate matter at the density found within a neutron star's core. Long before telescopes existed, human observers across multiple independent cultures occasionally witnessed a genuinely extraordinary celestial event. A new star, bright enough to be seen with the naked eye even during full daylight in the most extreme cases, suddenly appearing in the night sky where nothing had been visible before, then gradually fading away over the following weeks or months. Events modern astronomers now understand to have been supernovae, the same violent stellar deaths discussed at length in the first installment of this series, but observed and fully recorded centuries or even millennia before any scientific understanding of what was actually happening existed at all. The most thoroughly documented and scientifically significant historical supernova occurred in the year 1054, recorded independently by Chinese court astronomers, who noted a guest star bright enough to be visible during daylight for approximately 23 days, along with corroborating observations from Japanese and, according to some more contested interpretive evidence, possibly indigenous North American observers as well. Modern astronomers have definitively connected this 1,000-year-old naked-eye observation to the Crab Nebula, an expanding cloud of stellar debris located roughly 6,500 light-years away, at whose center sits the Crab Pulsar, a rapidly spinning neutron star completing roughly 30 rotations every single second, making SN 1054 one of the very few historical supernovae where astronomers can directly and precisely match an ancient written observation to a specific, still visible, still actively studied modern astronomical object, providing an exceptionally rare and scientifically valuable direct link between recorded human history and ongoing astrophysical research. A second, considerably less studied but independently well-documented historical supernova occurred in the year 1006, recorded by astronomers across an unusually wide geographic range, including observers in China, Japan, Iraq, Egypt, and continental Europe, with several contemporary accounts describing it as the brightest stellar event. ever recorded in human history up to that point, reportedly bright enough to cast visible shadows at night, and to be seen clearly during daytime for a period of several weeks. Modern astronomers have identified the corresponding supernova remnant, a rapidly expanding shell of stellar debris located roughly 7,200 light-years away, and detailed study of the remnant structure has confirmed 1006 as a CPAS supernova, the same specific stellar explosion category discussed in the previous chapter's white dwarf discussion, giving astronomers a genuinely rare opportunity to study, in exhaustive physical detail, nearly 1,000 years later, the precise aftermath of exactly the kind of stellar explosion still used today as one of the primary distance measuring tools underlying humanity's entire understanding of the universe's accelerating expansion. The astronomer Tycho Brahe personally observed and meticulously documented a third historical supernova on November 11, 1572, an event that carried genuine and immediate scientific significance well beyond its simple visibility, since Tycho's careful measurements demonstrated the new star showed no detectable parallax shift relative to the background stars, proving it existed far beyond the Moon's orbit, directly among the supposedly fixed and permanently unchanging stars themselves, a finding that directly contradicted the prevailing Aristotelian cosmological model of the era, which held that the realm beyond the Moon was permanently fixed and entirely incapable of change. Tycho's meticulous 1,572 observations, published in his own detailed treatise on the event, are now widely credited by historians of science as one of the pivotal early cracks in the older, Earth-centered Aristotelian worldview, helping open genuine intellectual space for the scientific revolution that would follow over the subsequent century, a direct historical link between one specific dying star and the broader transformation of how humanity came to understand the physical universe entirely. A fourth and, to date, the most recent supernova ever observed within our own galaxy with the naked eye occurred in October 1604, independently observed and documented by numerous astronomers across Europe, most thoroughly and most famously by Johannes Kepler, whose own detailed published account of the event, including careful measurements of its changing brightness over the following year, remains one of the most complete and scientifically valuable records of any historical supernova. What makes SN 1604, now commonly called Kepler's supernova, genuinely significant within tonight's broader video is a specific and striking fact. In the more than 4 centuries since Kepler's careful 1604 observations, no other supernova has ever been confirmed occurring within the Milky Way galaxy itself, and visible to the naked eye from Earth, despite the fact that current astrophysical models predict a galaxy the size and stellar population of the Milky Way should produce, on average, somewhere between 2 and 3 supernovae per century, a statistical expectation that has, for reasons that remain only partially and speculatively explained, simply failed to materialize as any directly publicly observed naked-eye event for more than 400 consecutive years. This genuinely puzzling gap, sometimes discussed among astronomers under the informal heading of the missing supernova problem, has several partial, non-mutually exclusive proposed explanations worth naming directly. A meaningful number of galactic supernovae occurring during this 4-century gap may simply have been hidden from direct visual observation by the Milky Way's own substantial interstellar dust, which is heavily concentrated along the same galactic plane, where the overwhelming majority of massive supernova-prone stars are also found, potentially obscuring an event that would otherwise have been clearly visible. Indirect astronomical evidence supports the idea that at least some galactic supernovae genuinely have occurred during this gap without being directly seen, most notably Cassiopeia A, a supernova remnant located roughly 11,000 light-years away that current dating techniques place at approximately 1,680 meaning the underlying explosion likely occurred at almost exactly the right time to have been visible. Yet, as far as surviving historical records from that specific period indicate, apparently went entirely unrecorded by any known naked eye observer at the time, a specific, genuinely frustrating near-miss for what might otherwise have been the actual most recent directly documented galactic supernova. Modern astronomers now rely heavily on neutrino detectors, including the same general category of instrument responsible for catching the historic 1987 supernova. Neutrino bursts discussed in the first installment of this series, specifically as an early warning system for the next galactic supernova, whenever it eventually occurs. Since neutrinos would escape a dying star's collapsing core and reach Earth's detectors hours before any visible light became detectable, potentially giving astronomers a genuinely unprecedented advance warning window to point every available telescope at the correct patch of sky before the visible explosion itself even becomes observable. A coordinated global alert system called the Supernova Early Warning System, or SNU, that has stood continuously ready and fully operational since 2005, waiting so far for 2 full decades. For an event that, based purely on statistical expectation, is somewhat overdue. Beyond the 4 galactic supernovae discussed above, one further historical event deserves inclusion here specifically because of what it represented for astronomy more broadly. On August 20, 1885, astronomers across Europe noticed a new point of light within the Andromeda galaxy itself, then still widely believed by most astronomers of the era to be a relatively nearby gaseous spiral nebula rather than an entire separate galaxy comparable to our own Milky Way, a fundamental misunderstanding about the basic scale of the universe that would not be corrected for another 4 decades. The object, later catalogued as SN 1885A, became the first supernova ever observed in a galaxy beyond our own, though at the time no one recognized it as such, and its actual significance was only properly understood. Retroactively, after Edwin Hubble's 1923 measurements finally established Andromeda's true, immense distance and its status as a fully independent galaxy, retroactively transforming what 19th century astronomers had recorded as a modest and only moderately interesting brightening within a local nebula into direct, historical evidence of a titanic stellar explosion that had actually occurred 2.5 million light-years away. A considerably more recent piece of historical astronomical detective work resolved a centuries-old puzzle in 2021 when a research team finally identified the modern remnant of a guest star Chinese astronomers had recorded in the year 1181, describing it as visible for roughly 185 days before fading, a supernova candidate that, unlike SN 1054, SN 1006, SN 1572, and SN 1604, had never been definitively matched to any known modern remnant despite more than a century of searching. The research team identified a fast-expanding nebula called Pa-30 surrounding an extremely hot central star as the likely remnant, and detailed analysis of its expansion rate when projected backward placed its origin almost exactly at the year 1181, while the object's unusual properties, including a central star that appears to have survived the explosion, rather than being fully destroyed, suggest 1181 was likely a rare type of thermonuclear explosion in which 2 white dwarfs partially merged without fully disrupting either star, making it, alongside the type IX zombie star explosions discussed in the previous chapter, a second confirmed historical example of a supernova that left something behind, rather than destroying its progenitor completely. Korean court records add a further, independently useful data point to the historical supernova catalog, documenting a guest star observed in December 1592 during the Japanese invasions of Korea, bright enough that court astronomers tracked its changing position and brightness over several weeks, even amid the considerable wartime disruption of the period. Modern researchers, cross-referencing these Korean astronomical records against Chinese and Japanese sources from the same window, have used the combined, independently corroborating accounts to refine the timeline of naked-eye galactic supernovae. And the broader value of records like these extends well beyond any single event, since pre-telescopic court astronomy across China, Korea, and Japan collectively provides modern astrophysicists with a genuinely unique multi-century, multi-culture dataset of naked-eye transient events, one no single Western European record from the same centuries comes close to matching in either completeness or continuity. A reminder that some of tonight's most scientifically useful historical evidence survives, not because anyone recording it understood what they were watching, but simply because they wrote it down carefully and consistently year after year. String theory emerged during the 1970s and 1980s as one of the most ambitious theoretical projects in the entire history of physics, an attempt to resolve the deep, persistent incompatibility between general relativity and quantum mechanics, already discussed in this video's chapter on the mystery of time, by proposing that the universe's most fundamental constituents are not point-like particles at all, but instead extraordinarily tiny, vibrating one-dimensional strings with a given string-specific vibrational pattern, determining which particle, an electron, a photon, or any other fundamental particle, it appears to be when observed at the comparatively enormous scales any real experiment could ever hope to probe. For the mathematics of string theory to remain internally consistent, avoiding certain deep mathematical contradictions that arise in a universe with only the three familiar spatial dimensions, plus time, the theory requires the existence of additional spatial dimensions beyond the three we directly experience, typically 6 or 7 extra dimensions, depending on the specific version of the theory. Under discussion, dimensions physicists generally propose must be compactified, curled up into shapes so extraordinarily small, far smaller than any particle physics experiment has ever probed, that they remain permanently undetectable at any energy scale currently achievable by human technology, while still exerting subtle mathematical influence over how the visible, familiar dimensions of our everyday experience actually behave. The specific geometric shape these hypothetical extra dimensions take on, when curled up in this way, is not, according to the mathematics of string theory itself, uniquely determined, and this specific mathematical ambiguity has produced what is now widely called the string theory landscape problem, arguably the single most significant scientific and philosophical controversy connected to the entire theoretical framework. Different physicists working through the underlying mathematics through the 1990s and 2000s calculated that the number of mathematically self-consistent ways these extra dimensions could theoretically be compactified, each producing its own distinct, internally consistent set of physical laws and fundamental constants, could plausibly number somewhere around 10 to the 500th power, a number so staggeringly large that, if each distinct mathematical possibility corresponded to a genuinely separate physical universe with its own distinct laws of physics, it would comfortably exceed even the already almost incomprehensibly large number of atoms estimated to exist within our own single observable universe. This landscape of possible universes has become, for a meaningful faction of contemporary theoretical physicists, directly and explicitly connected to the multiverse and fine-tuning discussions already introduced in the first installment of this series, offering one specific mathematically grounded mechanism through which an anthropic explanation for our own universe's apparently fine-tuned physical constants might actually work in genuine physical practice, reasoning that if all, or even a meaningful fraction, of these 10 to the 500th power mathematically possible universes genuinely do exist somewhere within some larger, more encompassing physical reality, it becomes considerably less surprising and considerably less in need of any deeper independent explanation that we happen to find ourselves within one of the comparatively rare universes whose particular combination of fundamental constants permits the formation of stars, chemistry, and, eventually, observers capable of noticing and wondering about any of it at all. This same landscape problem has also generated genuine, serious, and ongoing scientific and philosophical controversy over whether string theory, taken as a complete package, including its vast landscape of possible universes, actually qualifies as a genuinely testable scientific theory in the first place, a criticism most closely associated with physicist Peter Woit and, from a considerably more philosophical angle, Karl Popper's older and more general falsifiability criterion for distinguishing genuine science from untestable metaphysical speculation. Once upon a time, if string theory's underlying mathematics genuinely permit such an enormous number of distinct possible physical outcomes, critics have argued the theory risks becoming compatible with essentially any conceivable experimental result, a property that would, under a strict Popperian standard, place it dangerously close to the boundary separating genuine, falsifiable physical science from an elaborate, internally consistent, but ultimately untestable mathematical structure, a serious methodological critique string theory's own most prominent defenders, including physicists Leonard Susskind and Brian Greene, have directly and repeatedly engaged with over the past 2 decades, generally arguing that the theory's broader mathematical framework does still produce specific, meaningfully testable predictions, even if the precise details of which particular landscape vacuum which describes our own universe may never be independently verifiable through direct experiment. Supersymmetry, a specific and considerably narrower theoretical proposal, closely associated with, though formally distinct from, the broader string theory framework, predicts that every currently known fundamental particle should have a considerably heavier, as yet undiscovered superpartner particle, a theoretical proposal that would, if experimentally confirmed, help resolve the hierarchy problem discussed in an earlier chapter of tonight's video, and would additionally provide a genuinely compelling new dark matter candidate distinct from the WIMPs, axions, and sterile neutrinos already discussed across both installments of this series. Despite representing one of the most actively and expensively searched for theoretical predictions in the entire history of the Large Hadron Collider at CERN, extending across more than a decade of dedicated high-energy particle collision experiments since the collider's initial 2010 startup, no confirmed superpartner particle of any kind has ever been directly detected, a persistent and genuinely significant experimental null result that has led a meaningful number of theoretical physicists to grow increasingly skeptical of supersymmetry's most straightforward and most experimentally accessible theoretical predictions, even as more complex, harder to directly test variants of the underlying theory remain formally unfalsified and continue to be actively studied and refined. What makes string theory and its accompanying landscape genuinely significant to include within tonight's broader video, whatever one's own personal view of its ultimate scientific status happens to be, is precisely how directly and how starkly it illustrates the fundamental tension running quietly through nearly every single chapter covered across both installments of this entire series, a mathematically elegant, internally self-consistent theoretical framework built by some of the most capable working physicists alive today that may, despite decades of dedicated effort and genuine intellectual achievement, ultimately prove either impossible to conclusively test using any technology humanity could ever realistically hope to build, or, alternatively, may yet still produce a genuinely decisive and confirmable experimental prediction that current theoretical understanding simply hasn't identified or isolated quite yet, a distinction between unexplained and possibly unexplainable in principle that sits in its own quiet way near the very heart of everything this entire two-part series has been patiently trying to explore. String theory is not, it's worth noting clearly, the only serious contender currently attempting to reconcile general relativity with quantum mechanics. Loop quantum gravity, developed beginning in the late 1980s primarily by physicists Abe Ashtekar, Carlo Rovelli, and Lee Smolin, takes a genuinely different starting approach, proposing not that particles are secretly tiny strings, but that space itself is not smooth and continuous at the very smallest scales, instead composed of discrete, finite loops of quantized gravitational field, woven together into a structure sometimes called a spin network, meaning space would possess an actual smallest possible unit of volume and area, roughly the Planck scale, below which the ordinary concept of continuous space simply stops applying at all. Unlike string theory, loop quantum gravity does not require any extra spatial dimensions beyond the three we experience directly, and it makes at least one genuinely testable prediction that gamma-ray photons of different energies emitted simultaneously from the same distant cosmic event should arrive at Earth at very slightly different times after traveling across billions of light years. A subtle effect several gamma-ray burst observations have searched for without yet finding a confirmed signal, leaving loop quantum gravity, like string theory, itself mathematically serious and actively developed, but still without the kind of direct experimental confirmation that would settle the broader question of quantum gravity in its favor. A separate and more abstract idea, called the holographic principle, proposed independently by physicists Gerard 't Hooft in 1993 and Leonard Susskind in 1995, suggests something considerably stranger than either full theory on its own, that all the information describing everything happening within a given three-dimensional volume of space, in principle including every event inside an entire universe, could be completely and equivalently encoded on that volume's two-dimensional boundary surface, in roughly the same way a hologram encodes a full three-dimensional image on a flat two-dimensional surface. This principle found genuine mathematical teeth through the AD-FT correspondence, a specific and rigorously worked-out example published by physicist Juan Maldacena in 1997, demonstrating a precise mathematical equivalence between a theory of gravity operating within a particular idealized curved space and a completely separate quantum theory, without gravity at all, operating on that space's boundary, a result many theoretical physicists consider among the most important discoveries in the field since the 1970s, even though the specific idealized space Maldacena's proof uses does not, in its exact original form, describe our own actual universe's true geometry. String theory's landscape is not, notably, the only theoretical route physicists have proposed toward a multiverse of separate physical universes. A largely independent mechanism called eternal inflation emerges directly from the same cosmic inflation theory first proposed by physicist Alan Guth in 1980 that already explains the universe's earliest fraction of a second expansion, discussed in the first installment of this series. Physicist André Linde, refining the theory through the 1980s, showed that inflation, once it begins, may not actually stop everywhere at once the way simpler early models assumed, but instead should continue forever, in most places, with individual regions randomly stopping and bubbling out into their own separate, fully formed universes, each potentially governed by a different random combination of physical constants, while inflation itself continues indefinitely in the space between them, a picture in which our own observable universe would represent just one bubble among a truly unbounded number of others, continuously being generated, and in principle, never actually finishing. Unlike the string theory landscape, which describes a fixed menu of mathematically possible universes without directly explaining how any of them would actually come into physical existence, Eternal inflation describes an active, ongoing physical process for generating them, and a number of theoretical physicists have proposed combining the two ideas directly, treating string theory's roughly 10 to the 500th power landscape as the menu of possible physical laws and eternal inflation as the mechanism that actually populates each entry on that menu with a real, physically existing universe, a synthesis that remains, like nearly every other idea explored in this chapter, mathematically elegant and entirely untested by any direct experiment. We've spent tonight moving through 14 chapters and 300 new facts, entirely distinct from everything covered in the first installment of this series, from the leftover comets and asteroids still drifting through our own solar system, through the thousands of confirmed exoplanets, reshaping how astronomers think about our galaxy's total planetary population, into our own Milky Way's surprisingly unresolved structural puzzles, through the first confirmed gravitational wave detection and the strange, genuinely unresolved nature of time itself, past the ghost particles streaming silently through your body by the trillions, out through the highest energy particles ever recorded, and the antimatter that should have erased the entire visible universe before it ever properly began, through the small, persistent cracks appearing in some of physics's most precisely measured numbers, into the genuinely open and carefully contested search for life on other worlds, past strange and exotic stars and the ancient supernovae our own distant ancestors watched appear and fade in the sky centuries before any telescope existed, and finally out to the very edge of string theory's own staggering mathematical landscape. It seems fitting in these final quiet minutes to sit honestly with what connects all 300 of tonight's facts to each other, and, in a broader sense, to the 200 that came before them, in the first installment of this series. Nearly every single subject covered across both parts of this now 600-fact journey shares the same underlying shape, a phenomenon precisely measured, carefully and repeatedly confirmed through independent observation, and yet still, after decades or in some cases centuries of dedicated scientific effort, not fully and completely explained at the deepest level physicists would ultimately like to understand it. This is not, and has never been, across either installment of this series, a story about science failing or falling short. It's the opposite. It's a story about how much genuine, hard-won, carefully verified knowledge modern science has actually managed to accumulate about a universe that, at every single scale examined across these now 27 combined chapters, from the subatomic ghost particles discussed tonight to the largest cosmic structures discussed in the first installment, has consistently turned out to be stranger and more genuinely interesting than any single simpler explanation could ever fully capture. Some of tonight's specific open questions will likely be resolved within the coming decade, as instruments like the Vera C, Rubin Observatory, the James Webb Space Telescope's continued observations, and LISA's eventual launch bring considerably more precise data to bear on several of the specific puzzles discussed across tonight's 14 chapters. Others, including the deepest questions connected to string theory's landscape, the true nature of time itself, and whatever ultimately explains the universe's fundamental constants, having exactly the specific values they do, may genuinely remain open for a very long time yet, quite possibly, for considerably longer than any single human lifetime, including the lifetimes of the researchers currently working hardest to resolve them. There's a particular kind of comfort available in that thought, if you let it settle for a moment before drifting off. Every open question named across tonight's 14 chapters is being tended to, quietly and patiently, by someone whose entire working life is built around not needing an answer tonight, or this year, or even within their own career. The physicist recalibrating a neutrino detector 2 kilometers under the Antarctic ice, the astronomer reprocessing another night's worth of exoplanet transit data, the graduate student rechecking a gravitational wave signal for the 100th time. None of them are racing a clock you need to worry about. The universe has been patiently unexplained for exactly as long as anyone has been looking at it, and it will keep being patiently unexplained long after tonight, which means there is truly nothing left for you to solve, track, or hold on to before you sleep. That's not a discouraging note to close a long night's listening on. If anything, it's a genuinely steadying one. The universe does not owe anyone a complete explanation delivered on any particular timeline, and the scientists working through each of tonight's open questions, one careful measurement, one painstakingly designed experiment, one decade of patient data collection at a time, have never treated that absence of a final answer as any kind of failure. They've treated it, instead, as simply the ordinary, expected shape of doing careful work on a subject large enough to comfortably outlast any one person's own working career, and the fact that so much of what's covered across both installments of this series remains genuinely, honestly open is less a gap in human knowledge than a fairly accurate, fairly humbling snapshot of exactly how much careful, patient work remains quietly underway all around the world and off in orbit above it at this very moment while you listen. Once upon, you don't have to resolve any of it tonight any more than you had to the first time. You just have to let this second, longer accumulation of careful measurement and honest uncertainty settle over you the same unhurried way the first 200 facts did, the comets and the exoplanets, the gravitational ripples and the ghost particles, the antimatter that almost erased everything, and the ancient light from stars that finished dying centuries before anyone alive today was ever born, and let all 300 of them gently carry you the rest of the way down into sleep.